Rajesh sir, with your permission, shall we go ahead and start the session?
Yes, we can start. Means like if people have joined, then it's okay.
Means some have joined. I can see more than 100 now, and they are joining.
So then we can start. Not
Can
an
you
issue.
able to see the participants in the chat box, sir? Participants and the chat. I hope it would be visible to you.
We can start then. Like if participants are there, then we can start.
Yes, sir. So, welcome to the third day of the faculty development program on advanced optimization technique. Today we have with us Professor Rajesh Kumar, who has actually initiated this workshop on advanced optimization technique, and he has been working uh, in this particular field for last 2 decades. So he is an inspiration for all of us, and it is my pleasure to introduce you to the participants, sir. Professor Rajesh Kumar is the former head of Department of Electrical Engineering, MNIT Jaipur. He has received his BTech degree from NIT Kurukshetra and MTech degree in Power System and PhD degree in Intelligent System from MNIT Jaipur. He was postdoctoral research fellow at Department of Electrical and Computer Engineering, National University of Singapore, NUS, from 2009 to 11. Dr. Rajesh Kumar has interest in focus on intelligent system, machine intelligence, power management, smart grid, and robotics. He has published more than 500 research articles and has supervised 20 PhD and more than 30 MTech students. He has 14 patents to his name. He received 3 academic awards, 12 Best Paper Awards, 6 Best Thesis Awards, and 4 professional awards and 30 student awards. His articles have been highly cited by researchers all over the world. He is there in the editorial board of 12 international journal of repute. He has been an associate editor of IEEE Access, IEEE Industrial Electronics Technology News, associate editor of Swarm and Evolutionary Competition Elsevier, associate editor of IET Renewable and Power Generation, associate editor IET Power Electronics, and associate editor of International Journal of Bio-Inspired Computing and CAI Transactions on Intelligent Technology. Professor Rajesh Kumar is a senior member of IEEE, fellow of IIT, fellow of IE, fellow IET, life member of CSI, senior member of IAMG, life member of IETE. He was honorary secretary of IET Rajasthan chapter and XCOM IEEE Delhi, PES IAS, and vice chairman of IEEE Rajasthan subsection. So, with this introduction, I thank sir for again joining and motivating the participants. So, over to you, sir.
Yeah, thank you, Dr. Nanda.
Your video is not visible.
Yeah, I'll share my screen. Just give me a second. Yeah, I think the screen is visible to everyone.
Yes, sir.
Okay. So good afternoon to one and all, and today's our agenda for the discussion is
Sir, we
the
simultaneously streaming on the thing. So you, if it is possible, sir, kindly make it on.
what video you want to put it on?
Yes, sir.
Okay, I have to make a bit, just let me do that first. Okay, I can make it from this. Let me
Yes.
see if it is working.
Yes, sir.
Is it okay?
Yes, yes, sir.
Okay. So yeah, welcome all on this session on differential evolution and the variant. In this session, we try to understand the philosophy and then methodology of DE. Then we discuss some with the help of some numerical approach that how it works, and then we go for the variants which are being developed by various researchers in the community there. So this one is it is again a population based optimization algorithm introduced in 1996, and mainly it is developed to optimize real parameters or real valued functions. Before jumping into it, we can see the all kind of optimization approaches into three forms. There are three segments of any optimization, whether it's a classical linear optimization or classical non-linear or meta heuristic. There are three stages. The first stage is basically the first question is need to be answered is how to start, or where from where to start. So like in your classical optimization or deterministic, we have certain kind of values known to us. From there we start. In random based approaches, we initialize randomly and then we move further. So that is the first step in all the algorithms. You can check it. It is the first thing which we need to understand is basically uh, how to start with. Okay, so this one is the first step we do, always we do. Okay, so this is the first step, and then the second step from here we move towards is the policy to move. Okay, so we always look for a policy to move from one point to one segment to another segment, or from one solution to the another solution, or we are trying to find out the solutions because we are following certain kind of, maybe it may be a iterative or it may be some other approach, but there we look for these things, that what is policy to be adopted to move. And then the third step is basically then that is basically stopping criteria. So you'll find all these things there. Like if I talk about linear optimization, that okay, we normal or simplex method, we say okay, 0 0 is the point to start, and then we look for policy to move from one point to another point. And the policy that adopted is we look for pivot point and pivot row and column, and then we swap the values. And likewise, and the stopping criteria we follow is that okay, when all the uh, variables they are either positive or negative, we stop it, something like that. Similarly, in non-linear, we have some initial points which are given. So those are the points to start, and then we adopt certain kind of policy to move. So if my problem is differentiable, we find out the gradients, and then we move from one point to another one, and likewise. And then we have certain kind of stopping criteria there. The same thing is being followed in all kind of meta heuristic. So how to start is basically we initialize some population in most of the almost everywhere. Randomly we select those points. So that is the first thing, that is how to start. You just check it with your evolutionary algorithms, or your or your swarm based algorithms, or any kind of algorithm. So that is the one kind of thing which is, that is how to start. And then we adopt certain policy to move. So we try to understand okay, how to move from this point to another point. And that varies from algorithm to algorithm. Like in genetics, we use crossover mutation to move one point to another. In PSO, we go for looking or minimizing our distance with the personal best and the global best, and likewise. So you will find this policy there, and then the stopping criteria, maybe number of iterations or maybe the repetition of the solution or something like that. So in DE also, we follow the same. How to start is basically, again, since it's a population based optimization algorithm, so that is our start way. That is how that is starting. Basically randomize or initializing some population randomly. Policy to move, since it is a evolutionary uh, based approach, so we'll talk on the policy, what is the policy to be adopted there. And the stopping criteria can be either iterations or no repetition of the solutions, and likewise. So in D, this we use it to solve a nonlinear optimization problem. It is a stochastic approach. It's a population-based algorithm where we represent the population as some number, some individuals, and that means those are the all those individuals. They are the solutions. Okay, so all our solutions, their population means all the possible solutions, but but they, which one is the optimal one, that is yet to find out. So we try to find, we initialize with certain solutions, possible all feasible solutions, and then we look for what is the best solution there. So that is what is there, that we start with the possible solutions, and we uh, do iterations. It's a iterative process, and we follow 3 steps there. So that is the policy here. So we follow 3 steps uh, to to realize DE, and those comes under the policy. So one of them is the mutation, which is, you'll find most of evolutionary algorithms there. Another one is the crossover, and third one is the selection. So these are the three things which we find uh, in DE, and we follow step by step them. So looking towards the stages of the algorithm, you can see here we have first stage, which is the here. You can see the initialization of the vectors there. These are the initialization of the population, and then something is different here, but let's take it like this. This one is mutation, which is a part in evolutionary algorithms, but here we go for difference vector based mutation, and that's why the name is there, differential evolution, because we are taking the difference of the vectors, and we use this difference to develop the mutation operator there. And then we go for the crossover, same as in something like we are, I think you already done in genetic algorithm. And then finally selection, which one to be there for the next round of calculation. So that is again a very important part of it, that how to how to select the offsprings and the parents basically. So talking with the starting with the initialization. So initialization means we have variables. So if there are n variables, then it is n dimensional problem. So we initialize according to that, and for each variable there are certain limits. So say I have 3 variable problem, so there are, these are the 3 variables you can have, and there are oh sorry, then there are certain ranges of this one. You can say x1 you can vary in a higher range, x2 you can have a variation like this, or x3 it can be like this. And so these are the you can say upper bound of your variable, and this can be a lower bound of the variable. So each one is having a upper bound and lower bound, and we need to find out, we select our initial solution, or we select our feasible solutions only in these upper bounds and lower bounds. So this one is the condition we need to fulfill for all the variables, that the variable must be between the bounds there. And the easiest way to get it, to generate it, we can and since we are looking for random variation, so any variable can be, say, any value x variable, it can be taken as a very simple way, that is, we can take a lower bound value of that particular variable, and then we add a rand function in the range of 0 to 1, and then we put it upper bound minus lower bound. So if we follow this equation, then the things become very easy, because if my random value is 1, in that case the value of x is upper bound, and if it is 0, then it is lower bound, and if it is other than 0 and 1, you'll find the value is always between your upper bound and lower bound. So this is how we initialize the population there. This one is the starting point of it. Let's understand first the algorithm, and then we talk about various variants there. So then comes the second approach, which is second block, and that is known as mutation. So in mutation, you can see a few things which are very interesting to understand. There are three things which are very important. One is your, you can say, that is target vector. Second one is your donor vector, and third one is your trial vector. Okay, so let's understand the definitions. So a parent vector from the current generation is known as a target vector. Okay, and then your mutant vector obtained through the differential mutation is your donor vector, and then finally offspring is generated by combining your donor vector with the target vector, that is trial vector. So let's understand how it is working here in this case. So say you can see here this picture in front of you. You can see there are few vectors there which on which we want to apply this one. So say this one is the vector on which we want to apply the things. So this one is the initial vector. Okay, so then what we do normally in a basic D, we choose three different vectors. So you can see here what are those three vectors. I take another vector, which is another solution vector, which is this one. I'll take another solution vector, which is this one, and I'll take another vector here, which is this one. Okay, so these two vectors which are here, okay, these two vectors which are here, we find out the difference of it. So this is the difference you can see here, and that's why differential comes into the picture. And this difference then we multiplied by certain kind of a scale. Okay, so this vector which is in there, this multiplied by certain scale which is here, then we add it here. Okay, so this vector which is r1, so on your r1 we add the difference. I'll get a new vector which is here, which is your vector. It will be the next target vector. So this is how we modify it. So we take one vector or one solution on which you want to operate, and then we take another two more solutions. We take the difference of those two solutions, and then we multiply, or we scale it up, multiply it by scaling factor f, and then we use this f to do the mutation process. Let's understand it mathematically also, how it is working here. I'll come this mutation strategy later on, but before going to explain this process, we can take it, skip few of the slides, and let's understand the mutation part first there, so that we can realize the things, how the things are happening there. So say I want to minimize certain function. Okay, I want to minimize a function f, which you can say x1 plus x2 plus x3. This is a very simple. So initially you can see randomly I have taken six populations here. Okay, 1, 2, 3. Oh, sorry, this one is matter screen is very sensitive. So 1, 2, 3, 4, 5, 6, and randomly we have taken certain values here. You can see x1 value is taken, then x2 is taken, and x3 is taken, and we just evaluate it, that what is the function value. Similarly, a second set, similarly the third set, the fourth set, and fifth set, and sixth set. These are the different sets there. We can call them vectors also. Okay. So now my population part is ready. That is the first thing. That these are the basically black dots. If you recall your figure, these are the certain solutions there. Then what we do, out of these two, we randomly pick two of them. Okay, so say here we have taken this one and we have taken this one. Okay, and then we find out the difference between these two. So you can see there the difference is taken between 0.92 and 0.12. So I'll get this difference for x1, this difference for x2, this difference for x3. So this one is my difference vector. This one is my now difference vector. Vector means it is a representation of all the variables in one form. So this one is representing the difference of uh, vector 2 and vector 4. That is the second step which we do there. Then we move to the next one. We multiplied it by certain factor. Okay, so we multiplied it by certain factor, and then what we do, we add it to the another one. So what is this factor? Okay, we have taken some factor here. Okay, and we multiply it to the this difference is multiplied by this factor, and then we add it to the another one, another vector chosen from the same population. So from here it is I'll take this is taken here, and we perform it like this. Okay, so when you do that, we normally many times we call it as a noise also. So you can see these are the values of the vector 0.94, 0.63, 0.6, and 0.13, and the values are added is difference vector multiplied by f. So those values are added here. Yeah, multiplication, you just check it. This one is not correct. So we'll get a new vector here. So this process is consisting of two things. One is mutation and another one is cross and mutation. So this part till so far it's the mutation part. Then we go for the crossover. So let's move back and then understand what is a crossover and how it is working. Then we will come back to this slide again. So there are various ways to do the mutation. So mutation is basically what we are doing is we are adding some things, and what we are adding the difference of the two vectors and the scaled version of that one to another vector. So these are the various approaches. You can see there are 9 strategies are there on your screen uh, with different mutation strategies. So what is the meaning? You will find in literature, you'll find the representation like this. Okay, you will find the representation like this. Okay, so first is D, that means it's a differential evolution. The second one is the best. So best means we are going to add to the best value. So you can see here, if it is written here best means we will use the best vector, we will modify that best vector here. That is very important to understand here. And then the next sign, you'll find it is 1. The 1 means we will take a single difference here. So this is the single difference, and always the difference is multiplied by some scaling factor. And then we have another term at the end, that is exp. We'll discuss on this one. You'll find everywhere either exp or bin. This is basically we talk about the crossover. When we perform the crossover, we use exponential approach or binomial approach to perform the crossover. So this one is the notation. So you can see in the first one, we are modifying the best because it is written best here. In second one, it is written that RND to best and 1. So you can see that randomly taken certain value. Okay, and then we, so some one value is taken here, Okay, so this one is a bit different in the case, and then here it has to be written best here also. So one of this value, this one is basically just correct it. This one is just 1 second. It is not working. Let me correct it. So we will take it as best. So what we will take, we take a random value which is to be modified, and then we are modifying this one as a difference of with respect to best with lambda plus some difference of other two vectors and scaled with f. Best 2 is a bit different. You can understand we are modifying the best value which is here, but 2 means we are taking two differences. So you can see here difference between this and this is one difference, and this one is another difference. So we are taking two differences, and then we multiply it by f. Similarly, you can have uh, uh, rand 2. So instead of best, we put a rand here, random value, and two differences here. Similarly, best one, and likewise. So this is how the researchers propose different mutation strategies. They either they modify the random value, like the example I have shown, that randomly we have taken one value and then we add the scaled difference to that one, or if not so, then they have taken the best value and then they modify the best value there. So this one is basically how the mutation is being done in differential evolution. Then the next part is your crossover. Okay, so the crossover is basically we put certain kind of a logic there. What we this one is you can have a crossover rate here. This one is CR, and then we just generate a random number, and we'll see if the random number is less than CR. We modify the next value with the earlier one, and if it is more than that, then we will not modify. You can see here, you can see that these two are like this. Say this one is the old one, this one is the new one, and we keep on checking every time the random number. You'll see that if your random number is less than CR, your this old value which is here, it is modified by the new value, and if the value is not um, it is greater than CR, then the old value remain as such. So this is basically how this crossover is being done, and CR is known as your crossover rate. So there are various other various approaches are also being adopted in this scenario also. So this one is your crossover rate, and this one is a binomial crossover rate. So depending upon your random number, we will see whether that particular feature is taken from the mutated one, or not to be taken. So this is how the crossover is being done, being adopted there. And then the last part of it is basically that is the selection part of it. Selection is basically we compare the two. Okay, the old value on the old function values. You can see here it is f is written. So whatever the function value, and then we compare with the new function value. So whichever is better, we keep that one and discard the rest. So this one is nothing but just why we are comparing the children and the offsprings, and we'll see that which one is good. If the children is better function value better than the parent, then the parent is replaced by the children, else the parent remains in and children is out of the calculations. So this one is basically the selection, because what we are looking towards, like, all the total number remains same. Otherwise, if it is not being taken, we cannot keep both parent and the offspring there, uh, because that will then that may stop my algorithm, because every time we are taking the difference there, and uh, if they are being taken of the same values, then they may create issues, because the algorithm may stop there. Graphically, it's very easy to understand from this figure. You can have a random vectors, random vector A, random vector xc, random vector xb. You can you take these two vectors, find out the difference of xb minus xc, scale it up. Okay, once it is scaled, then add it to the random vector. Then you perform the crossover. because this is your target vector. You perform crossover, and then from you have a trial vector, and there you can perform the selection whether this trial vector is better than this. Then this trial vector comes here, else this vector comes here. So this is the selection criteria. So this is how this algorithm works. Okay, this one is a pseudocode available in all the research articles and everywhere. If you check it, it is again the same. We initialize the population here and the various coefficients. Coefficients are like problem size, population, mutation rate, crossover rate, stopping criteria, upper bound and lower bound, and then we check out who's the best vector there. Then we select the random vectors there. Then we apply your find out the difference, multiplied by the f value, add it to the another value, we'll get in this one, and then from there we go for the crossover. You can see here whether we need to go for this or that, and then at the end we'll check it out, which one is the better. We keep it, and if that is not better, we new solution is not better, then we keep the old one for our calculation. Okay, so this is what we have already discussed here till so far. That okay, random again. Let's check it this way. Okay, 1 second. I don't know. Yeah, something wrong is coming. It's moving very fast. Yeah. So we have taken vectors here. I'll take another color. So these are the vectors. So this one is sorry, this one is vector. We evaluate at the bottom. This one is another vector. We evaluate at the bottom the third vector, and likewise. So we have 6 vectors. We choose randomly 2. Here we find out the difference, that is here. We multiplied it by some scaling factor, and then we add it to the another taken vectors here. So this process is over, and then we go for this crossover part here. You can see here the target vector is the first vector, so the first vector values are here. Okay, CR we have fixed for our calculation, that okay, what is crossover rate is 0.5. This is the solution which we have obtained from here. So this is the solution which we have obtained here, and then we randomly what we do, we take the first variable, generate a random number, and check it whether that random number is less than 0.5 or not. If it is less than 0.5, so then this value will be the added to the solution, and then we check the next variable and check it. So say the random number is more than 0.5, so then the old value comes here, and for the last one again it happens, so this comes here. So this will be the new vector here, and then I put these values into my function and then evaluate it. So if this new function value if I evaluate it, this value will be function, we know that. So this will be 1.58 plus 0.89 plus 0.04. So this value is very but obvious more than 1.116. So we keep the old one parent as it is, and we discard this calculation. Then we go for the next one. We take this one as a parent, and we repeat the whole process. And this process keep on repeating. This is how this whole algorithm works. I hope we are able to get it. So now this is the basic algorithm, and the next thing is what are the parameters which govern my algorithm. So there are various parameters which govern the algorithm. Population is one of them. Your CR, crossover rate, this one is another one. Your F vector, this one is another one. Mutation strategy, that is another one. So there are various factors which govern or control the convergence or the solutions and of this particular algorithm. And then the researchers try to modify, try to uh, adopt certain kind of strategy so that they can find out the best possible value of these parameters. And those are the variants which we can see in the literature proposed by many of the researchers. So we can modify these parameters by various ways, and the most common ways are the three. These are the three most common ways. One is your deterministic parameter control. We use deterministic approach to control the parameters, and basically these are the parameters: your Fs, your CR, your population. Also, another one is there, which is your mutation strategy. And these parameters, controlling these parameters means we are controlling your exploration and exploitation. And you'll find this term is being commonly used in almost all the meta-heuristic or nature-inspired algorithms. So one of the approach is your deterministic approach. The another approach is your self-adaptive parameter approach, and third one is your adaptive parameter approach. In deterministic parameter approach, we fix it with certain kind of number. Okay, uh, this is how I'll change my F, CR, or NP. So, or these are the values I'm fixing it. And adaptive parametric control, what is there? It is basically the values are when we try to modify your F, CR, and NP. Uh, it's not from the population itself. The modification policy or modification methodology is outside. We and then that policy we use to modify this value of your F, CR, and NP in every iteration or after certain iterations. If we talk about self-adaptive, then it can be, we can say that uh, then your variation or modifications or adoption in your F, CR, and NP is controlled within from the population of the algorithm. So these are the three approaches which are being used to control the parameters, and they generate certain kind of variants. Let's see few of them. Okay, so deterministic parametric control is there. You can see here like we fix the range for F, we fix the range of CR, and then we are not taking any feedback from the evolutionary search. We are taking we follow certain kind of a deterministic rule. And that okay, initially I'll start with F is equal to 0.4, and after 10 iteration I'll make it 0.5, then after another 10 iteration I'll make it 0.6. So I'm following some certain kind of that approach. If I'm changing it, and if I'm not changing, I just fix certain value. So that is there, and one of the popular algorithm is CODE, that is a variant, that is composite DE algorithm. So what is the philosophy or methodology adopted in CODE is like this. Okay, so a trial vector is selected from the set of groups. Okay, and the main objective is to merge trial vector strategies with the different parameter settings. So what they have done is like we have three strategies here: rand 1 bin, rand 2 bin, and current to rand 1. And these are the certain parameter settings being taken there. Okay, F is equal to 1, F is equal to 1, F is equal to 0.8, crossover is 0.1, crossover is 0.9, crossover 0.2. So now we have three mutation strategies, and we have three set of value of F and CR. And what being done there is basically kind of crossing the things there. Okay, so like the first trial vector strategy is first kind of mutation with the first control parameter setting, then first with the second setting, then the first with the third setting, then second mutation strategy with the first setting, and likewise. So all combinations being tried there, and then we are looking for uh, what is the best solution there. So this one is something like kind of some part, means like not exactly, but it is a very small example can be taken like ensembling kind of combinations. We have different combinations, and we are looking for which one is performing better. So this one is one kind of variations people have developed. So this one is algo, which is already available. I think I'll go to the next one. These pseudocodes are already there in research articles. Uh, then comes the adaptive parameter control. I'm taking the popular one. I'll discuss only those. Rest you can check from the literature, but just try to uh, put that whole methodology or algorithm on what we are discussing right now. So in adaptive parametric control, you can see a lot of variation, a lot of algorithms are there, because now people think of that, okay, it's always better if we have feedback of the evolution strategies and policies, and then we use that feedback to modify our parameter that will give better solution or something like that. So the approaches are being developed are like DE with self-adaptation populations, and then fuzzy adaptive DE, then self-adaptive DE, then self-adaptive NSDE, self-adaptive parameter settings in DE solution, adaptive DE, and these are the variations which people have developed. Few of them we will discuss right now. So one of them is like differential evolution with self-adapting populations. So the name is DESCP. Okay, so it dynamically adjusts the crossover and mutation parameters. They just give a different notation, but don't go for these notations. Just understand it that they use they dynamically or they keep on changing the crossover and mutation properties, and in certain experiments like De Jong's exam problem, it performed better than the rest of them. That is a claim basically in their own in the base paper there, where the mutation factor F, that is scaling factor, that is static. Okay, so and then what we do here in this algorithm, sorry. So this is 1 second. Sorry. This one is going a bit fast. So this is what they have done in their algorithm. They fix the value of your mutation factor, and your other crossover and crossover, they keep on changing. Uh, Crossover, they keep on changing, and they follow certain kind of a distribution. And that is normal distribution they have followed for this particular algorithm. The second one is your fade, that is fuzzy adaptive differential evolution. So what is the difference here? You can check it from here, that they have used a fuzzy logic based mechanism to find the value of f and cr here. So they split the data, and then the objective function they try to implement into the objective functions, and then objective function we receive solutions, and then those solutions they pass through a fuzzy logic box, uh, which use fuzzy based theory to find out, okay, what is the value of f and cr, and then this value of f and cr acts as a feedback and go back to the d, and then that these things keep on working there. So this is FAD they have developed. So you can have better idea from here. We initialize the population here. We fitness evaluation is there. Condition of termination. If it is no, it goes here, and then we change the setting of DE using the fuzzy theory, and then this keep on working there. So the purpose of using fuzzy logic is to make the DE control parameters adaptive in minimization process, and so so and the minimization error between the global minima and actual function value, in case of knowing about the global, if we have. So I mean, this one is kind of a learning kind of thing. So say if we have certain idea of minimization value, so we keep on minimizing the error between the global solution and what is being received, and and change the parameters accordingly. So that is basically FADE variant. There is another variant which is being used, that is SADE, which is self-adaptive differential evolution. So what is being done there? There are two mutation strategies being used here. You can see here. One is DE rand 1 and another one is DE current to the best, and then we assign some probabilities to this one. So that is the another part, that is if probability P1 is the 1, so then the second strategy is 1 minus P1, and then uh, accordingly the new generation is being developed here. So the flow is like this. Population is generated, and then for if any vector, if the value is less than P1 random value, if it is less than preset values, then the first strategy will be applied, and otherwise the second strategy will be applied, and then all the trial vectors, they are evaluated, and based upon their solution the new probabilities will be calculated, that P1 and P2, and likewise these things keep on repeating. So the factor here is like we have two probabilities and then we are putting conditions on them. So this strategy, if you try to go into depth of it, it is basically more like grouping of the population, and that okay, based upon some kind of the strategy is not uniform for all the population. Strategy changes because we generate a random number, and we'll see that whether the random number is less than that particular probability. If it is less than that, then we adopt certain mutation methodology. Otherwise we go for the different mutation methodology. So this basically depends upon that one. And here the P1 and P2, they keep on changing because they are evaluated every time depending upon how the solutions are being generated there. This one is another approach, which is self-additive NSDE, and that is basically here uh, you can see here your mutation strategies. It is basically a different. So uh, what is the difference? Difference comes here. It follows your Cauchy distribution rather than the normal distribution. In the first one, when we talk about, that was the normal distribution, but here the Cauchy distribution is being adopted there. There is another popular algorithm which is self-adaptive parameter setting in DE, which is known as small JDE. You can see the policy here. So the policy is adopted there. That is 0.1 to plus 0.9 into random number. If random number is less than some coefficients here. Okay, so we fix these coefficients, and then we depending on the random value, we'll get the values of your scaling factors. So they are modified in that particular ways there. In adaptive DE, AD, you can see here some variations. You will find how your CR is being changed. Either you can see the CR is a function of certain parameters. Not only can be, you can see the in exponential part your here only the CR part is changing, and that is how this CR is being controlled. So this one is, if you check it carefully, these are similar, something like in PSO also we have linear decreasing inertia or exponential decreasing inertia or stepwise varying inertia. Similar kind of stuffs are being adopted by various researchers in differential evolution also. In modified D, your F is modified by the Laplacian distribution. So we have example where we followed normal distribution, then we have Cauchy distribution, and here it is a Laplacian distribution. So uh, likewise we can adopt some another approach also. Then there is another modified D with P best crossover. So here you can see here the mutation strategy is a bit different. Here you can see your X best is being used for the correction factor. There are two differences here, so which are not a big, but one correction factor is the difference of with XG best is taken, and then P best is recorded, which one is the best so far, and that is being used again in the calculations. F is also varied here, 1 over by 10h function. These are the certain another coefficients which you'll find in the literature, that how these are controlled. Crossover rate is varied between the maximum value and the minimum value with a certain function of the certain as a part or with a certain new functions there. Then another one is very popular because we have only 8 minutes, so we'll go fast. So that is JADE. This one is basically here we have something interesting in a form. These things are almost same. You can see here we taking difference, one difference multiplied by scaling factor. This one is difference with the best multiplying by the scaling factor, and we have another kind of a solution here. You can see something is being adopted here. The difference comes into the picture. We follow certain kind of a greedy strategy here. uh, uh, Methodology is same, DE current to the P best 1. Okay, so the greedy method is being adopted here uh, because we are incorporating our best. We are so right from the beginning we are trying to minimize or trying to bring this vector, this difference vector as low as possible, and this one is the best value. So that means we are trying to move as close to the best value very fast. So the difference we are always taking with the best. So that is basically greediness present there. And then uh, it may lead it in certain cases it may lead to some kind of premature convergence also, or trapping into the chances of trapping into the locals. So there people adopt put another vector there, that is v3-g, which is being used here as a randomly combination of your new and old values. So this one is new value and this one is the old value. So this is new and old means you can say offspring and the parent. So that is how this combination is being taken there. We can have multiple strategies. So that is what basically we can say uh, what we can do here in this case is we can make an ensemble. We take 3 or 4 strategies there, put the parameters, and then we apply all the 4, and then we keep on evaluating which one is performing better. So the best of those 4, the solution obtained, we'll consider it for the next solution. So that is basically kind of a combinations we can do it, and those are those comes under this category that we have multiple strategies of mutations there. People try to combine, try to make hybrid of these things, like they try to combine D with PSO. So here you can see till so far is D works here, but you'll find PSO is being here. Okay, and that is a certain kind of a condition. If not fulfilled, then the new solution is generated by using PSO and kind of that stuffs. So that is basically how you are combining with PSO there. There are other various combinations people have adopted to combine already existing algorithms. Like you can see here, uh, DE and ABC people, they have combined, try to solve a multi-objective planning problem. DE and ACO, that's a single objective real optimization problem they have just implemented. These are the authors. And then DE with the BFO, bacterial foraging, and DE with the gravitational search, DE with the IWO, invasive weed optimization, D with Firefly algorithm, D with fireworks. So there are a lot of such combinations you can observe in the literature where people try to combine DE with some other approach, and they uh, try to make hybrid. So two things can be done here. Either seed is taken from D and then applied to the second algorithm, or seed is taken from the second algorithm and applied to D. Like seed is taken from GSA and or PSO and then given to D for to find out the solution. The other way is also possible, that the seed is taken from D and then passed to uh, second algorithm, maybe say Firefly, to generate the solution. So this is how some people have tried to develop some hybrid approaches. So yeah, in a very small time, I try to just to put the basic and how people are trying to modify the or develop the variants and various combinations of D they are using it for their particular purpose. So I try to present all the things in a very compressed manner. Yeah, any questions, you are most welcome. I'm open for your questions so that we can have more discussion on it. Yeah, thank you very much. I think I'm in time.
Thank you, sir, for giving such a nice presentation and explaining about the DE, its variants, its combination with all other algorithms. You have explained all the equations involved in step-by-step manner with example, how to generate the difference equations and all. So it is a very nice lecture. So if you will have a look at the chat box, sir, and try to answer
Yeah,
some of
I'm
this one's query.
just trying to see it and like, okay, chat box. Just give me 1 second. Uh, okay. There's I think only one question rest are PP about the PPT and all that. That why the factor is taken as 0.08 or so. See, yeah, now the questions are coming. Okay, for that example, it is taken just to show you that how it works. But other than that, I have shown you many of the variants people have developed. How and that is basically a very important area of research also, that how to find out the best value of f to get the most optimal solution. So one way is you just fix it and then yes, process your things and get results. The another way is you can adopt any deterministic kind of approach, that okay, I'll start f with this value and after every iteration I keep on reducing. So that can be the solution, one of the way to choose the f. And the third one is okay, depending upon how you are obtaining your solutions, based upon that you can make your f adaptive. And that's how people have developed various variants uh, only on the variation of the f. Though other factors, yeah, yes, population and crossover, they are there, but uh, this is how people have taken. So in today's example, it is just taken just like that, just to show you that how it works, what is the where it is being used. Question is, we can we apply D for clustering? Yes, clustering is again an optimization problem. So you convert any problem to a optimization problem and then check it whether the problem is uh, complex enough. Yes, you can apply D, because this one is an optimization approach to get your solution. So there you can use it. Means any optimization problem you can apply your D to get your best solution from there. And then optimization target can be anything. It can be a number of cluster. It is the optimization problem. It can be some other parameters like intra-cluster distances and all that. That is also an optimization problem. So you can use this algorithm, not only this, any optimization algorithm to solve a problem. Any more questions?
Sir, there is one question over here, that how
Yeah.
the modified D is better than the existing D algorithm in terms of performance measures.
Yeah, see, when you apply D on any problem, and say you just fix your crossover rate and your scaling factor and your population, you reach to certain kind of a solution, and we are not sure whether, and that is really a challenge. We don't know whether it is the best solution. So and we also know at the same time that these values CR and F, they control your two uh, basic requirement of any meta heuristic, that is exploration and exploitation. So we don't know what should be the optimal value. and if we fix it, it is very likely we are not reaching to the best solution. So what people have adopted, they follow some strategy that why not to take a feedback from the solutions and the population basis. So population is nothing but a solution. So why not to take a feedback from the solution in every iteration and make our these coefficients adaptive, keep on changing so that we reach to the best solution. So that is one justification that why these adaptive coefficients perform better than the fixed value DE algorithms.
There is one more generalized question that how to handle constraint in these population-based algorithms.
So the best thing is when we are evaluating it, when we are generating the population, that is the best place you check it whether there is no violation of constraint, because I told you that each variable is having its range, upper bound and lower bound. So generate the things from there only, and then one another thing which you can do, which sometimes it happen that when you are generating a new solutions that like in D, after your mutation crossover we have new solutions. Again check it whether they are violating your bounds or not. If they are violating a bounds, then discard it, and then you can follow a new policy that how to replace that particular population, that particular value to a new value. So many like people have adopted, some people are using PSO, some are using simple approach. Simplest approach is uh, if your new value is violating your bounds, just throw it away and randomly generate a new value within the bounds. So though there you can follow certain kind of a strategy, but that is the easiest way to handle your constraints there, because constraints are always on the variables. So we need to, and variables means the population values there. So we need to check it. Initially you check it, and then after every iteration it's good to have a look on it. If anything is violating your constraints, just discard it and add a new in place of that.
There are no more major questions I look into. So thank you, sir, for giving such a nice presentation.
Yeah.
We have your sessions also tomorrow and further in the next week as well.
Yeah. We'll see, and next week we'll see if we can implement some real problem or use some code, how it is solving or analyze it. So that will be great. Yeah, tomorrow we'll discuss some different type of meta heuristic. Yeah, that's great. Yeah.
Thank you, sir.
Yeah. Thank you.
Participants.
Yeah. Thank you, Dr. Nanda, and thanks everyone for listening. Thank you very much.
Participants, now we have a very important announcement that we have sent you a Canvas link, and how to join in the Canvas platform. We will be explaining you now. And in the Canvas platform, you have to give the quiz, which has been scheduled on this Saturday, 11th, one quiz, and Friday, another quiz. So you have to appear in the quiz to get certified in this particular program. So please accept our Canvas link. And in the Canvas link also, every day's presentation, you can by yourself able to download it easily. And all the things have been given in the Canvas platform. So now we will be demonstrating you how to use the Canvas platform step by step. I request Dr. Illa to elaborate on it.
Hello everyone, good evening. As Sir said, the Canvas link has been sent to everyone. It has resended 2-3 times. And if you're not finding it in your inbox, you can also check it on promotional and the spam folder too. Sometimes it happens that it came to these folders. So let's start with it. How the Canvas link can be operated. You will be having one link, and after that, you have to log in yourself. Okay, you have to create your account there. So if you originally having your account, so this program, this AOT FTP can be listed there. But if you don't have any Canvas account yet, so we can build it. There is a two-way of doing it. Either go to this canvasinstructor.com login, this link, or you can create your free user account from there. Or you will be having this kind of a mail invitation, course invitation. This is the link which we are talking about, that we have sent the invitation from our end, and you have to click here. So you have to click this get started button. So it will land up you to here where these two options will be showing up: get a free Canvas account and request a live demo. So you can opt both of them. I would suggest click on a get a free Canvas account there. And after that, you will be having this window where you have to log in with your credential or you have to create one. So there is the option, the marked one, the black marked one, the sign up option. You just click that sign up option. And after that, you will be landed up to this page where you get a free Canvas account here. Again, you have to click it. Then this is the credential which you have to put, the name, the organization, the phone, and the email ID, and everything, the information that should be entered by you for creating it. And after that, by putting this next button, click on this next button, and you will be landed up to this. This window will be open to your Canvas account. Then the course invitation will be represented like this, that you have been invited to this program. Okay, so here it will be 2021 Advanced Optimization Technique and hands-on MATLAB. So as a student, so you have to accept this invitation. Okay. So in this way, when you accept it, you can be observing that in the left panel, we are having so many options like this home syllabus. I have indicated this quizzes here. So it is very important to log in your Canvas account, because all the quizzes will be performed here. All the materials, the PPTs will be shared day wise. So you can easily download it from here. And also the quizzes, like here in the screen, you can see the quizzes button. If you click it, so you will be landed up this currently test quiz is displaying, and you have to click it here. Okay. So in this way, next is take the quiz and you can perform your quiz. So quiz is very important for evaluation purpose. So you have to be there for this quizzes, you have to opt it. So this will be look like this. In the question one, this objective minute will be running. So it will be only possible if you log into your Canvas account. So as I explained, two ways are there and you have to do these things. Thank you. And if you're still having any doubt or problem for logging into it, you can contact us. Okay, now we will take a short 5-minute break, and after that we will resume with Bansal sir. I think Bansal sir has been connected with us. Good evening, sir.
Good evening, Jagdish sir.
Good evening. Good evening. I joined. So yes, just let me know whenever we'll start. I'm ready, right?
Sure, sir. Sure.
Okay.
So participants, now there is a break for you. Jagdish sir, are you there? Hello.
Yes. Hello.
Welcome, sir. Welcome, sir.
Thank you so much. I hope my video and audio are clear.
Sir. I am giving you the presentation.
So there are two places. So give me to Jagdish Bansal. Right. There is one JC Bansal. So not to this, to Jagdish Bansal, right? Whose video is not on. Give the right to that.
One is JC. This one. Sir, we have made you the presenter. The ID Jagdish Bansal.
Yeah, just a second. Yes, now I got it. Should I start?
Yes, sir. Yes.
Okay.
Audio and video both are perfect, sir.
Okay. So good evening again, everybody. I hope yesterday the algorithm artificial bee colony was clear to everybody, and today another algorithm in the same category. If you remember yesterday, I was talking about the classification of the algorithms, the derived algorithms and the inspired algorithm. And among the inspired algorithm, I said that broadly, I say it is swarm intelligence and evolutionary computation. And in swarm intelligence, I'm going to cover this ABC and today SMO. And in evolutionary, tomorrow I'm going to cover biogeography based optimization, another algorithm. Actually, many other algorithms have already been covered in this category. Differential evolution, just Professor Rajesh has covered. PSO, you said that already. Sorry, not PSO here. ACO is done, and the GA in this category has been done. So today I'll discuss on this SMO. So spider monkey optimization. So, you know, the name itself suggests that there is a spider and there's a monkey. No. Yesterday itself, I said that the swarm intelligence, in the swarm intelligence algorithms, the swarm must be made of homogeneous individuals. Means all should be same. All the individuals are same, homogeneous individuals. So of course, spider monkeys cannot be. Actually, this spider monkey is a particular kind of species of monkeys, which is called spider monkeys. And they have a very special kind of foraging behavior. Very special kind of foraging behavior. And this foraging behavior is simulated in terms of a computer algorithm. And we call this spider monkey optimization algorithm. So look, in ant colony optimization, in ABC, in PSO, in GWO for gray wolf optimizer. In all these algorithms, the foraging behavior is modeled. Foraging behavior is simulated. Foraging behavior means how they forage, how they search for their food. This is the behavior which is explored, which is simulated in terms of computer algorithms. So similarly, the foraging behavior of spider monkeys is simulated in this algorithm, and the computer algorithm is obtained. Okay, so look, I told you that in among the spider monkeys, actually, I have not mentioned it here. It's a 1 hour lecture, so I removed few slides. Spider monkeys is a special kind of species which live in the deep forest. They have a very special kind of foraging behavior. They share the information by barking or some physical gestures. So they say that I'm here, you are there, I have this much food and so on. So, you know, like yesterday I was talking about the sharing of the information, the language of beach, that is the dance. So today the language of sharing of the information is the barking. They bark in different styles. Right. So based on that, they share the information with each other. So what information they share, how this information is analyzed, and how this information is means they respond to the information. After analysis, how they respond to the information. You know, per day I got I think 20-30 emails of conference, workshops, this, that this is the conference, submit paper here, attend this, go here, go there, 10-20. But I hope you understand, everybody is informing me, sharing the information with me, but whatever is suitable to me, whatever that particular conference is suitable for me, I will attend only that. I will submit the paper to only that conference. I will attend only to that workshop. Try to understand what that getting the information is. It is not necessary that you respond to the information. So similarly, in spider monkeys share the information with each other, honeybees share the information with each other, but it is not always necessary that you immediately respond as they say. Means as X says, it is not necessary that X dash will move in that direction. It is not necessary. If X says, suppose that this is your direction. Suppose X is one spider monkey. It says that this direction is a good direction, and X dash is here. X dash is here. This is X, which is, and there is another X trick also, which is saying that this direction is good direction. So now it has actually not only X's direction, it has X trick direction also. You know, he's getting the information from all. Let me just call the information. He's getting these information from both. Means 20 emails I'm getting daily about the conferences, but it is not necessary that every conference I submit a paper or every conference I attend. I will attend only the relevant conference and the most efficient conference also, most reliable conference also. So similarly, the X dash will respond to only that information which is relevant to it, which is good for it, right? So how they analyze, how this X dash monkey, this monkey will decide that X trick information is good for me or X's information is good for me, which information is good for me, and if I have decided that X trick information is good for me, then how to proceed this time? Should I believe it 100%? Should I believe it 100% or not? 100% means if this X trick says that this is a good direction, should I immediately start it in this direction, or I should take some balanced direction? Like in PSO, if you remember, this is your current position, and this is the direction of G best, and this is the direction of P best. Suppose, then in PSO, what happens? You take the vector addition. Vector addition means if C1 R1 equal to C2 R2. If both are same, then this vector, this is your resulting vector, means X will take this direction. X will take this direction in PSO, because it is getting the information from two members, right? P best and G best, and finally it is getting this direction. It is not believing on G best, it is not believing on P best completely. It has analyzed both the information and realized that I should go in this direction. Of course, if this is changed, means if this R1 is different generated, you know, these are R1 and R2, so different values. So it is rarely, this is the rare case. In most of the cases, one will be less than other, right? In that case, this vector may be inclined towards this or may be inclined towards this. Means anywhere this is the direction. I hope you are getting my point. In ABC, this information is shared like this. This is your random. So it goes to this or goes to this, either to this direction or to this direction. If the random number is negative, then goes to this direction. If it is positive, then goes to this direction. So they move in this way. Remember, in ABC, you are getting the information from randomly selected members, so you are deciding accordingly. In PSO, you are getting the information from GWAS and PWAS, you are deciding accordingly. In differential evolution, you are getting the information from the experience of two randomly selected members. Of the two randomly selected members, XR1 minus XR2, and that too only DE rand one strategy. If it is 2, then the differentials are 2, means 4 vectors are there. So based on the 4 positions, you are deciding your own direction. Ultimately, all these algorithms are actually different mechanisms to move from one position to another position. So, you know, in all these algorithms, you take any algorithm, they are getting the information from the nearby people. Now these nearby individuals, maybe the G-based, maybe the P-based, maybe the random, or maybe the combination of random and P-based G-based, or maybe the combination of random and G-based. This depends how you have defined, how you have developed your algorithm. And then get the information and then proceed towards that. Now this equation changes. In differential evolution, the equation is different. You take like this, it means of course you generate the offspring, one parent vector you generate. For every parent vector, you generate another parent vector, which is called the trial vector, right? So x let me call it u, right? So x1 plus f, that's a scaling factor, and x2 minus x3. So this x1 may be the best, depends upon the strategy. So, you know, these equation varies. Like if you have this strategy, just imagine, actually why I'm discussing this, so that you can understand that how the researchers are developing new algorithm. You can also think of developing new algorithm, provided you understand the idea behind this. You know, this equation is developed. So this is your randomly selected. This is one differential for this one. Now this may be the best, means the new parent, the another parent. For this parent is generated actually, so that they can do the crossover later. So this u is generated either based on the base solution, either based on the randomly selected, and this differential. These differentials are again varied, rand to best, and so on, right? So here again in differential evolution also you can write, instead of the two randomly selected member, you can write some G-based or P-based like them. And who said you take the inspiration from differential evolution and use these kind of strategy in PSO? You increase one more term in PSO, you increase one more term in ABC, you increase one more term or decrease one more term in SMO, and so on. So, you know, all these algorithms has different update equations, but the idea is same, that take the inspiration from community members. And who will be the community member who is going to inspire you depends algorithm to algorithm. Okay, so just let me know if I'm not audible, you know, or is there any problem? Just let me know. Okay. What I said is they have a special foraging behavior, and this special foraging behavior is called the fission-fusion social structure, or they live in a society. Spider monkeys live in a society. You know, the humans live in a society, ants live in society. Similarly, spider monkeys also live in a society. They looks like this, and they have very special kind of foraging behavior, which is called the fission-fusion. And oh yes, I forgot to mention that this algorithm was introduced in 2014 by our group. I'm the one, and another is Dr. Harish Sharma, Dr. Simpi Singh Jadon, and the Maurice Clark from France, who has one remarkable work in PSO. So we 4 people worked on this algorithm, means we developed this algorithm in 2014. There is a website also of this algorithm. You can visit later this algorithm smo.scrs.in. Let me write clearly so that if you want, you can visit this website. So from there, you can download the research papers or research paper on this, the codes in Python, MATLAB, and C++, right? Okay, so fission fusion social structure is the major idea behind this algorithm. This is the main idea behind this algorithm, that they live in the group of monkeys, means they live in a society, around 50 to 100 monkeys live in a society, and this group is always led by a female monkey, female spider monkey. This is always led by a female spider monkey. This is always led by a female spider monkey. So 50 to 100 monkeys live in a society. And what is the special in this? This is called fission fusion. And what is this fission fusion? Just hold on, I'll tell you. In short, I'll in the next slide, I'll explain this in detail also. But just in short, you know, a group of monkeys is there. They start food foraging. They started they start eating the food. If there is a scarcity of food, they divide themselves into smaller groups. This is your group 1, group 2, group 3, group 4, and so on, right? So they start this process is called the fission. This process, fission means the division among the small groups, right? And then they start in different directions. So all the groups search in different directions, and in the evening again they come at the tree wherever they live, and this is called the fusion. This process is called the fusion. So fission and the fusion. Let me explain you this in detail. So this slide, I think, is one of the most important slide of this algorithm. If you are clear on this slide, I tell you that foraging behavior is crystal clear. Not always algorithm. I'm coming to that. But provided this slide is clear, you will be crystal clear with the inspiration behind this algorithm, right? So look, there is a group. This is your step 1. There is a group of monkeys. They may be 50 or 100, and this group is led by a female leader. Let me tell you that in swarm intelligence, please don't mistaken that in swarm intelligence, this is the necessary condition that there should not be any central control. Means no leader, no control, no king. All are equal, homogeneous. I started with this statement that all the individuals are homogeneous. And now I'm telling you that there is one female monkey who is the leader of this. It's a centrally controlled system. But let me tell you, no, it's not a centrally controlled system. If in the nature, nothing is centrally controlled. Everything is autonomous. Let me tell you, in the nature, everything, if you observe the nature, this is the God's creation, Parvala's creation. So how the power can be given to a single, anybody who has the strength, commands for some time. Means right now the power is with Narendra Modi of India, and there will be someday the power will go to somebody else. It was with somebody else earlier. So, anybody who is powerful will get the power, and as soon as he becomes not performing, the power transfer to somebody else. This is not, I think you agree that this is not a central control. Central control means, what is the name of that North Korea king? King something, right? Kim, right? North Korea king. That is called the central control. Nobody, you are able or not, but you are the king, right? So that is called the central control. But here, this female leader is the one who is the best in the group. Who is the best in the group? So I'll be happy if you just like somebody, Manish mentioned the name of the king, Manish Paul. So yes, it is good if you people keep on responding on the chat and not privately. do not send the private message to me, just send in public to everyone, right? Send to everyone. This will just ensure me that you are listening. Okay. So a lot of monkeys are there. They are controlled. They are led by a female monkey, and this female monkey is not, self-designated. It is the one who is the best in, who has the best information. The leader means having best information. Remember this: having best information of the food source, of the food. I hope this you will understand, that any monkey who has the best information. Today I went in this direction, I found this food. Somebody else said that I went in this direction, I found this much food. Now suppose this second one's food is better and higher as compared to this, then this second becomes the leader by default. I hope now you understood. Whoever is the best becomes the leader, right? So this is called the leader, female monkey, and this leader is known as the global leader, right? Because this is the leader of the entire group, and let me denote it by this. And this global leader, you may understand, similar to the G-best in PSO. You may call it like G-best in PSO, right? G-best in PSO, so global leader, right? Best of the swarm, best of the swarm, that is the leader. Now what they do under the leadership of this, because he has the best information, under the leadership of the global leader, they start food search. They start food search under the guidance of him. Under the guidance of him means all the monkeys for all X are attracted towards XG, G-best right now. In PSO what happens? X always attracts towards the compromised position, the balanced position towards P-best and G-best. Here, when the G best is there, means the single group is there and the leader is there, then under his guidance all the monkeys are working. It means he's influencing everybody. Means in the update equation, X G minus X is a good idea, is a good direction, right? If they are influenced by the G best, because here the vector is from, I hope yesterday I told you, this is this vector. Yesterday I told you that AB vector equal to OB minus OA, right? So XG minus X means XG vector, means the direction is from X to XG, means if I'm not the best one and other one is the best, so let me follow him, right? So XG vector. Okay, so they start food foraging and they found food source. Because he has the best information, they found food source, they start eating, right? Start eating. But what can happen? This is a large group. So after some time, it may happen that the available food is not enough. Whatever the food remaining is not enough for the entire day, for the entire group. So if it happens, then the global leader divides the group into smaller groups. This is one very important property, and this process is called the fission. So what we will do, we will divide the entire group into two parts initially. In the real world situation, it may happen that initially they may divide themselves into three groups. But in our algorithm, we have decided that we will divide into two groups, one by one, So here they divide themselves into two smaller groups. Now what happens? That leader, you remember this leader led by this initial group. Now he has to join one group. So this leader had joined, suppose this group. He had joined this group. So they are searching in different directions, different regions. So it may be that they may not communicate in real time. This group is communicating in real time. This group is communicating in real time within the group, but they may not communicate in intergroup communication, may not be real time communication. And therefore it is required that this group should also be led by another leader. So whoever is the best leader in this group, best monkey, in this group becomes the leader of this, and one of the group will have the same leader, the global leader, right? Now, since there are two leaders, so now we will not call them the global leaders, we will call them the local leader, one local leader, and this is also a local leader, but this is the one local leader who is the global leader also, right? I hope you're getting my point that these are the local leaders. Now the local leaders, global leaders means you have divided the entire population in terms of the algorithm. You have divided the entire population into two small groups which are led by different GBESTs, right? Now I'm calling them the local leaders, and they are searching in different directions. Actually, this is very beneficial idea. This fission process is very intelligent idea of monkeys, and which makes this algorithm very intelligent also. Actually, what happens when there is a large population, 100 population? Why in swarm intelligence algorithms you always try to take less population if it can work? If you take 500 population, it is always good. But what is the problem? Can anybody mention in the chat? What is the problem? Over 100 population and 500 population. Over 500 population, what is the problem with the 500 population or the swarm size? Yes, you're right. Kamlesh Raghuvanshi is perfectly right. No, I'm talking about the swarm intelligence, not the food agent. Okay, so this 500 is the duration of the time. Algorithm will take more time. Algorithm will take more time in the communication. Suppose 3 members are there, then the total connections are 1, 2, 3. 3 connections are there for fully connected structure. If there are 4 members, then you see 1, 2, 3, 4, 5, 6. 6 connections are there. This is your 3 connections. For 3, you just have increased one population. One member you have increased, and the number of connections are now 6. Try to understand my point that the communication time, the time complexity of the algorithm will increase. If it is a fully connected structure, fully connected topology you are using for the algorithm implementation, then it has to process 6 connections, 6 calculations. It has to process 4 calculations. You are three. You have just increased population size from 3 to 4. The connections, the processing time doubled. If you increase from now 4 to 5, then you can just calculate by yourself. It will be even many times more. Try to understand the time complexity of the algorithm will keep on increasing, exponentially increase if you increase the population size. And so, but what will happen here? Even with the large population, what is the benefit? If your algorithm is not working, now how I defined if not enough food, how I defined the not enough food. Not enough food is defined in terms of no update, like in ABC. Now you refer that ABC concept. In ABC, you remember there was a situation that solution is not improving up to 100 iterations. Yesterday I was talking about the sysfall story. So up to 100 iterations, the solution was not improving. Then in ABC, what was the thing you were doing? Scout B phase you were implementing. Of course, here what I'm doing, I'm not implementing Scout B phase, but the condition is same. Not enough food means the solution is not improved. And then I'm making the fission, means then I'm dividing the entire population into 2 small groups, G1 and G2, group 1, group 2. I'm dividing into 2 groups, and the one group is searching in different dimensions. Second group is searching in different dimensions. Now I hope you understand the time complexity will reduce. You are searching parallelly into small groups. Just imagine a situation that 100 people are searching in a ground by informing each other. And if the 5 group people are searching in the same ground by informing just 5 people, and the 5 people are informing each other, and the leaders of these smaller groups are communicating with each other. So only 20 people are either here that only 20 people are communicating with each other, and here only the 5 people are communicating with each other. Overall complexity will be reduced, and still the entire search space is searched. In fact, better way, because the influence will not be too much. Here in the global leader, case, the influence is very high. Influence is very, very high, but here the influence is relatively less. So the chances of misguidance is less. Chances of misguidance is less. I hope it's okay. Now, so smaller groups start foraging in different dimensions, different directions, and again, if suppose this small group will not get enough food, then this will again further divide into smaller groups, and all these smaller groups will have the leaders. And remember, not enough food means here this leader is not improving. Here this leader is not improving. Here not improvement of the solution means the best solution is not improving, right? So whenever the best solution is not improving up to a certain number of iterations, again the same concept of ABC, that some limit is there. Some limit is there. You know, everybody gives the limit. Bhagwan Krishna gave the limit, so the algorithm should also give the limit. So this algorithm is allowing the limit, and this is a parameter. This is a parameter which user has to decide. Usually in ABC it is 100. Here also it is 100, 50 to 100, 50 to 100. This limit, when this global leader is there, then the limit is different. And you know, there is a limit for this also. There is a limit for this also, and then the limit is different. So here there are two types of limit: global leader limit and local leader limit. Remember, GLL and LLL. Local leader limit and global leader limit. There are two limits here, and the roles and the actions are different. If global leader limit reached, the action is different. If the local leader is limit, action is different. In ABC, what happens if the limit reached? The action is scout B fetch. But here the actions are different. For local leader, action is different. For global leader, the action is different, right? Okay. You know, in real world situation, what happens? This local leader becomes the global leader for this small group for time being, right? So he has the rights to divide this group into further smaller groups. But in my algorithm, we have not given. I hope you understand, these are the inspired algorithms. They are not the exact simulation of the situation. Just for the convenience of the algorithm, the convenience of the implementation, we can always alter the phenomena, and always you can think of modifying this concept. But right now what I have implemented, that this local leader does not have the rights to divide this into smaller groups. Only the global leader, this is the global leader, which is also the one local leader. Only this has the right to divide into smaller groups. This local leader, if not improving, will change its search strategy, right? Will change the search strategy. And this global leader has the right, only the global leader has the right to divide for the fission. Remember this very important concept, very tricky concept. Only the global leader has the rights for the fission, and if the local leader limit reached, then the local leader alter its search strategy. And how the search strategy is changed, I'll tell you. So again, this process continues. This is called the fission, right? So fission is based on the, I hope you understand now, the condition for fission is not enough. Condition for fission means not enough food, and which is equivalent to solution not improved. Right now, the condition for fusion. Condition for fusion, and let me tell you, in the real world, the condition for fusion is evening. Whenever it's an evening time, sunset time, they return at the habitat. whatever is their habitat, they return their place. So this is called the evening. But in algorithm, how we make this equivalent? So the maximum number of groups formed, in the real world situation, whenever there is an evening, the fusion means they all go to the habitat, they all go to that particular tree wherever they live, and they share the information with each other. I'll tell you that. But in the algorithm, what we did, how the condition for fusion is determined, the maximum number of groups are found. Yesterday I was talking about the I think not here, sorry, not here I was talking. There is a condition on the minimum number of individuals in the swarm to have the swarm intelligence. Swarm intelligence cannot be achieved with one or with 2-3 people. The swarm size, if 2-3 swarms intelligence may not be achieved. You can see one of my blog is there on Medium. I wrote there in detail the minimum swarm size with PSO. I did some experiments, and the minimum swarm size should be 10. Actually, mathematically I derived then it is 12, and when experimentally done it is 10. So usually 10 is the minimum swarm size. Only then you can have a good swarm intelligent behavior. And therefore, what we did here in the SMO, that there should be some minimum number of monkeys in a group. If every monkey is, if the fission continues, then at last what will happen? A single monkey will remain, and if the single monkeys remain, many prey are there in the forest, they can kill the monkeys. They are, the group is the strength. Group is the strength of the monkeys. Group is the strength of the monkeys, so they live always in minimum size group, and this minimum size group is your maybe 10. I actually usually it should be 10. So if suppose total population is 110, suppose total population is 110, and I say that minimum number of monkeys required for this for one group is 10, then I hope you understand, then the total groups will be, maximum groups will be 11. Minimum monkeys are 10, total groups will be 11. Or if I will not define the minimum number of monkeys, then of course I can always define the maximum number of groups. It's the same thing. If maximum number of groups are this, then the minimum population will be 10, of course, right? And therefore, the fusion condition is the maximum number of groups are formed. If yes, maximum number of groups are formed, yes, then make a fusion, make a single group, and they return at home. After returning of this is one iteration. This is one iteration. After returning here, what happens? They share the information with each other. These monkeys share the information with each other. All the local leaders, there are many local leaders now. Suppose the 11 local leaders share the information with each other that I went in this direction, and this is the food amount. This is the fitness, F1, fitness function value, objective function value, right? So this is the food amount. And he said that this is the food amount. He said that this is the food amount. Now, whoever has the best food location, information about the best food location, he will become the global leader. He will become the global leader for tomorrow morning. You just imagine how intelligent they are. What is happening here? They are searching in different directions. And if they would have gone in a single group, they would have searched a small region of the forest. But since now they search different in a smaller groups, they search relatively large area of the forest, and they are sharing this information with each other for better food location, and this helps them to find the best food location in the forest, and of course the best solution location, right? Best food location means the best solution, the true optimal solution. So this is the foraging behavior of spider monkeys, and this is converted to an algorithm. Most of the things I already told you, that how we converted these concepts into the algorithm, the fission and the fusion, right? These two concepts, how we converted them to in terms of an algorithm. Now the next question is how to influence. Like in PSO, the birds are informing each other, fishes are informing each other, but how they are informing, that equation is written, right? In the honeybees are how they are informing based on the probability and all, right? How in the spider monkeys they are. So let us start with that equation formation, that how they're sharing the information with each other, what kind of equation we should develop. So the first is the initialization, like any other algorithm. I think no need to tell you, this is the same formula like ABC, PS, ODE, whatever the algorithm you take, this is the same formula. Random initialization in the range minimum to maximum, whatever is the range, you generates the solutions. And let me explain you that ith spider monkey is denoted by SMI. So instead of X or Y, I'm denoting it by SMI. I hope this notation is clear. Then there are certain phases, like in ABC or in PSO, there are certain phases here. First of all, the local leader phase. Let us start with the local leader phase. Here, this local leader, right now, this local leader, if of course, if there is no local leader, no other leader, then this local leader becomes the global leader. You know, if there is only one group, then this local leader is also the global leader, right? So initially, when there is no other group, this local leader phase is the global leader phase also, right? So, but I'm considering in general that there are groups, right? So the local leader phase, here the position is updated using this formula, new position equal to old position plus. This is influenced by the best solution. Of course, this is the best solution. I told you like xg minus x is a good idea. So yes, it is a good idea. And in this case, it should be positive. The coefficient should be positive. The direction should be this. The local leader influence is there. But this local leader influence, like in PSO, may misguide you. You know, you cannot blindly follow it. You cannot blindly follow it. Use your own mind also. And the mind is that you just keep on watching nearby monkeys also. You know, somebody told that, okay, you go and see the Jaipur is the best city to live, right? And I started from Delhi. I started to I packed my luggage and I started to Jaipur. In between, I saw that okay, there are many other cities also, right? Should I explore this also? So similarly, actually, this current solution is also influenced by the randomly selected solution, like in differential evolution or in ABC. So they are influenced by a randomly selected solution also. And of course, whenever you write, remember, whenever you write any randomly selected solution, you cannot always go towards it. Randomly selected, so it may be worse or better. So the coefficient is -1 to 1. Social influence, right? So in the local leader phase, the solution is updated using this formula, right? Now, how this formula is implemented, how the complete local leader phase is implemented. For each member SMI of the kth group, there are many groups. I'm considering, right? If it is only one, then one group. For each dimension, what you will apply, how you will apply this. If this is subject to a probability, that is called the probability perturbation probability. So I mentioned it here. Oh, it is not mentioned here. Okay, I'll let you know that this. I will give you more detail of this perturbation probability in the subsequent slides. So perturbation probability, this is subject to the perturbation probability, that if random number, any random number between 0 and 1 is greater than or equal to PR, then this is implemented. Otherwise, it will not be implemented. Otherwise, it will remain same. You see that in ABC, you know, this idea is actually reducing your time. It is not always a good idea to change your location, not always, right? So if some threshold should be there, so that this is the threshold, that if the perturbation rate is more than this threshold perturbation probability, only then I will change the position. Otherwise, we'll continue with the same position. In the global leader phase, what happens? Solution update their positions based on the probability, which is a function of fitness. Now look carefully. The solution here is updated based on the local leader. Simultaneously, the solutions are also updated, but this time it is not the perturbation probability, but this probability is entirely based on the fitness of the solution. Entirely based on the fitness of the solution means the fitter solution, the better solutions are given more chances for the update in the global leader phase. If there is a solution who is not good, will not get the chance to update itself in the global leader phase. This will again save the time of means start the solutions and will save your time to make your solution better. Okay. So what I said, the equation is same, just this instead of this local leader, you put here the global leader, and the probability instead of the perturbation probability, this probability is used. And I hope you understand this formula. This is very easy. The minimum probability is 0.1, means always 10% members will update, right? Even if the zero probability is zero fitness is there, the 10% members will always update. Otherwise, there may be a stagnation. So some members are updated always, and the remaining 90% members are updated based on the fitness. I hope you understand, the more the fitness, more the probability. Okay. Next phase is the global leader learning phase. Global leader learning phase. After updating the positions from the local leader phase and the global leader phase, what is the learning? What is the learning? And there are two types of learning now. One is the global leader learning based on the global leader phase, and one learning is based on the local leader. So I call them the global leader learning phase and the local leader learning phase. What does it mean? That the global leader will learn something, the local leader will also learn something. Means after applying the local leader phase and the global leader phase, the global leader will check what should I do, the local leader will check what should I do, right? If there is any action to be taken by me or not. So how they decide their actions. Position of global leader is updated by applying greedy selection, right? Greedy selection. What is this greedy selection? Look, if you have two solutions, X1 and X2, and their fitnesses are this, if this fitness is better, then X1 will survive. And if this fitness is better, then X2 will survive. Means whoever is a better solution out of two, that solution will survive. So this is called the greedy selection, right? And there are many types of selection. Those who have studied genetic algorithm must know about the tournament selection is there. Roulette wheel selection is there. That roulette wheel selection is very popular. So right now, you may think of applying the roulette wheel selection in SMO instead of the greedy selection. Just now it came into my mind that instead of greedy selection, we can explore the roulette wheel selection also here, right? And then we can see if there's a improvement in these. So, these kind of small changes can make your research paper, your new research paper. Spider monkey having best fitness is selected as the global leader. I already told you, no central control. Whoever has the best fitness will be selected as the global leader. If no update, if the solution is not updated, then the global leader limit count, GLL, I already told you, global leader limit incremented by 1. You increase it by 1. You increase it by 1. And how the local, and look, this is only a learning phase. It's not a decision. What to be done? Learn to take the decision, right? Learn to take the decision. Now, it is incremented by 1, selected as global leader. Now, how this global leader is going to behave, what the action it is to be taken is another phase, right? Global, that is called the local leader decision phase and the global leader decision phase. So the two phases are more, and then the algorithm is done. So the position of local leader is updated by applying greedy selection. Again, same here also. If this is your updated and this is your old position and this is updated position, check the fitness, whichever is better, will survive, other one will die out. Okay. The best solution is selected as the local leader. I already told you, no central control in the local groups also. If no update, then the local leader limit is incremented by 1. Here also there is a limit. There are 2 limits, local leader limit and the global leader limit. I hope I'm okay till now. There is no problem. So can you just type me that things are clear till now? So the next phase is this local leader decision phase. Next phase is this local leader decision phase. In the local leader decision phase, I already told you that the rights have not been given to the local leader for the fission. Remember, rights have not been given to the local leader for the fission. For division, the local leader is not designated. Local leader limit has been reached, then they will alter the search strategy. So what is the new search strategy? The very simple idea, and the logic is also very simple. Since this strategy is not working, you remember this strategy was there, LL minus SM plus U minus 1 to 1 and SMR minus SM. This was the strategy. I hope you know this screen writing and on writing on paper it's different. So these are the random number between 0 and 1 and local leader minus current position, random number between -1 and +1 and random minus SM. Random minus SM. This was the position. So if this situation is not working, limit has been reached, it means the solution is not updated up to a certain number of times, up to 150, 10, whatever you have taken the local leader limit. So that solution is this strategy is not working. So you need to alter this strategy. So how this strategy is changed? Instead of influencing from the local leader, it means local leader has lost its credibility. Means now the local leader no more the leader, and the solutions are getting influenced from the global leader, from the global leader. Also, like in genetic algorithm, sometime this random addition, in the real coded genetic algorithm, RCGA, if you have studied, in the mutation means you have a solution and plus some small randomness. So that small randomness addition means this time this local leader lost its credibility, means it is not helping the population. So this is the time of introspection by this local leader, means you are not a good one now. So why not you move towards some randomly selected member? You leave your position, move towards some randomly selected position and check whether you are good or not at that time. Whatever is your experience is not working. So why not you take some random actions, some random experience, right? And this time you see this is very important and thoughtful coefficient. Instead of -1 to 1, I put it 0, 1. Means even if it is random, I put it 0, 1 just to ensure that the local leader make sure goes to some random position, because the current random position is not working. Current local leader position is not working. Simple ideas, and you have a new search strategy for local leaders. For in a smaller group. So instead of that equation in the local leader phase, now this equation will work if the local leader limit reached. I told you that local leader has no rights to divide the group into smaller groups. And it is implemented with the perturbation rate, that if perturbation it is greater than or equal to perturbation rate, then it is implemented. If not, then this strategy is implemented. Now the global leader decision phase. In the global leader decision phase, the search strategy is not modified. He is the ultimate boss, so he has the right to divide that particular group into a smaller number of groups into smaller groups. So in this phase, the position of global leader is monitored. If it is not updated up to a predetermined number of times, then the global leader limit, we call that the global leader limit reached, and we divide the entire population into smaller groups. Firstly, the population is divided into 2 groups and then 3 groups. Means if one time the global leader limit reached, total number of groups are 2. Then the total groups will be 3, and they will be reshuffled. Remember, reshuffled, 3 groups. Again, then 4 groups. Means I'm increasing the number of groups one by one. I'm increasing the groups one by one, so that the global leader stagnation is not there. You know, there's a very, very intelligently designed condition that, you know, if stagnation is there, doesn't mean that you divide the entire group into 10 groups. No, there may not be need. It may not be need. It may not be required, because, you know, then immediately there may be an argue. There may be an argue that you told that smaller the group, less the computational complexity. So why not you make small groups from the beginning? Yes, less the time complexity, but immediately less the efficiency. Large the population, more the efficiency, So in search of saving the time, you are compromising with the efficiency of the algorithm. So here it's a compromise situation, balance situation, that initially I have not compromised with the efficiency of the algorithm, but when it is really required, this strategy is not working at all, then I divide into smaller groups, which is making my algorithm efficient. Which is making my algorithm efficient, and the accuracy is, of course, the information sharing is less as compared to this. So of course the success rate, the ability to search at the solution will reduce, but simultaneously that the time, the total taken time will be reduced, and the another area of the search space is explored. Okay, so each time in GLD phase, means global leader decision phase, local leader limit process is initiated. Local leader learning, sorry, this means local leader learning. Local leader learning. What does it mean? You know, if you are dividing the entire groups into 2 groups, then of course this local leader is to be decided. Here the local leader is to be decided. Local leaders are to be decided if you have a global leader decision phase. So every time you are implementing GLD, local leader learning is initiated. In case of which maximum number of groups are formed. Now, even if the global leader limit reached, and the maximum number of groups are formed, you know, already. So the global leader cannot further divide into smaller groups, and at that time, what it will do, it will make the fusion, form a single group, So throughout the algorithm, it is doing a fission, and then it is doing the fusion, right? So it is called the fission fusion social structure based algorithm. And it is implemented like this: if the maximum number less than maximum number of groups, divide the population; if not, combine this is your fission, apply the fission, otherwise do the fusion, right? And so on. This is the complete algorithm. I just summarized here the entire algorithm here. So all the phases are just written here, nothing special. Now, actually what I said, what should be the maximum number of groups? It's a parameter. So usually it should be n by 10. I told you about this 10, that I did some experiments and I found that minimum 10 members are required to form a good, to have the swarm intelligence. So this means it ensures that minimum 10 members are there in each group. Global leader limit can be decided by this n by 2 to somewhere n by 2 to 2 by n. So suppose you have 100, so 50 to 200. You can keep somewhere 50 to 200. It is recommended. And the local leader limit, you can keep d into n. You have 2 population size and 100, so 200 or something you can keep. Right? Of course, you should not remember, you should not keep the local leader limit and global leader limit is small numbers. Otherwise, what will happen? It will not become the Lord Krishna. Your algorithm will not become the Bhagwan Krishna. Your algorithm will become the Taliban. That one mistake and shoot, right? So what will happen then? Chaos will happen. Your algorithm will become a random search algorithm, right? One mistake and shoot. One mistake and do the fusion. Do the fusion. No, you give the chance, sufficient time. Let the algorithm work. Otherwise, the algorithm will remain. Otherwise, your algorithm will remain the will become the random search algorithm. And this perturbation probability is this is just based on the numerical experiment, so it can be somewhere 0.1 to 0.9, 0.2 or 0.3 is a good choice. Okay, and is the swarm size, I already told you. Okay, now there is some I know the time is up, so just I take 1 minute more. And here I have explained you that why this box, because the local leader phase is used to explore and the global leader phase is to exploit, right? So exploration and exploitation are better maintained, and here the stagnation is rarely possible, because whenever there is a stagnation for the local leader or global leader, you are always taking action, right? Right. So premature convergence is rarely happens in this algorithm, but when you are taking so many steps here, this makes this algorithm slow. No free lunch, NFL, no free lunch theorem, you remember. So since so many steps you are taking here, and this makes your algorithm relatively slow as compared to the DE, as compared to ABC, as compared to PSO, this algorithm is relatively slow, right? This is a drawback of this algorithm. But if you want accuracy, go with this algorithm. It gives you relatively better accuracy than these algorithms, but slow. So I have also explained you why this is different. What are the examples? When you have enough time and you want higher accuracy, go with this algorithm. It is highly cited, one of the good cited algorithm. Now there is a web page, I already told you, smo.scrs.in. So you can download the let me just quickly tell you that how to do this. Can I type here SMO? So okay, you just after this lecture you see that, right? There are many publications on this algorithm, and that's all. I have this numerical example also on this. Where it is, just a second. This is your example, but right now time is not available. I will share it with you. You can read this numerical example, so the remaining things will be crystal clear. Even if there is any doubt, the things will be crystal clear. I have given detailed discussion on of this algorithm in this also, so you will have I think no doubt in this algorithm. I will share it with you now. That's all from my side. You just let me know if you have any question. So,
Sir, for explaining the steps in very much detailed manner of spider monkey optimization algorithm in very closely step by step, everything you have narrated. So I request you to just have a look at the chat box and if possible.
so I can see there are questions. What is the local leader? Is it like master slave policies are in this year? Okay, yes. For time being, it's a master slave, but let me tell you, this master slave concept is not allowed in Swarm Intelligence. So I cannot absolutely say that it's a master slave. Master is the one who is the best. So like it is a G best, right? So yes, master means whoever is the best is the leader, right? Is the master. How can I make my basics in this area of niche inspired optimization algorithm? I'm feeling difficulty in studying such algorithm from research. Can you suggest me? Yeah, I can share my book with you. You drop an email to me. I will share my book on this. I have one book on this. So 3-4 algorithms at least you can see from that, or you can see my web page. There I have uploaded few resources, some video lectures. On YouTube also you can search. Usually I explain the algorithm with the help of examples. So you can see there, you just Google my name, you will find my web page. There resources is there, one tab resources is there, so you can see there the material, right? The slides are there, video lectures are there, you can always see that. I'm from mathematics, BSc, MSc background. So Kamlesh Raghuvanshi, yes, I'm also BSc, MSc mathematics background. I'm also MSc in mathematics, right? I'm not an engineer. So, you know, it says that one who know mathematics know everything. Generally, it's said. So you can study very easily these algorithms if you know the mathematics. During fission process, is there any criteria followed by global leader? During fission process, is there any criteria followed by global leader used for making groups? Yes, you are right. Very good question. Actually, really, thank you so much. Nitika Barwa asked this question that during the fission process, how the global leader is deciding. So suppose the 100 members are there, and the global leader has to divide them into two groups. So randomly 50 members are selected. Right now, let me tell you, I have implemented in this way. But again, Nitika, just because of your question, immediately one research idea comes in my mind that you people can think of some strategies, some criteria of making groups. Means there may be one group of best solutions, top 50 solutions. There may be one group of top lower 50 solutions, and there may be another idea of this making groups is that you can take the top solution one this side, and the next top solution this side, then the third best solution this side, fourth best solution this side, and so on. You can also take the top 50% solutions, top 50% solution, and make the OBL, opposition based learning. There is a formula you can Google after this. Based on opposition based learning, you can make remaining 50% here, and these lower 50% can be killed, can be removed, right? So there may be many strategies here to divide this group. Yes, this is a good question, really. And I never thought in this way that how to make some strategy. And I took this randomly actually in the original algorithm, but this is really a good idea. That the entire group can be divided into smaller groups based on different strategies. Yes. Can we use it in deterministic model, especially in dynamical system? Dynamical systems means, Chetna Singh, which kind of dynamical system you are talking? Dynamical means dynamical optimization problems. You are talking about dynamical optimization problem, or I could not understand this dynamical system. Means you are talking about deterministic model. It's not a model, actually, it's an algorithm. So, and I don't know what you want to ask. Toxicological. There's a very specific your research area, I think, and I cannot answer.
So dynamical system especially is in dynamic optimization, the problem statement changes with respect to time. So
yeah, that is okay. Yeah, that's why I asked that.
Yes.
If it is dynamical optimization, so it's a time dependent system, and this algorithm can be applied for the dynamical optimization problems as well. Yes, very much it can be applied, but I'm sorry I cannot comment on this toxicological dynamical model systems. I'm not aware of this. So yeah, if it is the case, then yes, it can be applied. And yes, deterministic models. Yes, for all kind of deterministic models, these algorithms can be applied. Yes, you are right. Now I got your problem. Now I got your question, Chetna Singh, that you want to say that the deterministic model for a dynamical optimization problem, can we apply this algorithm? Yes, yes, definitely we can apply this.
Sir, thank you, sir, for giving such a nice presentation and answering all the questions the participants have raised. So we'll be again listening to you tomorrow.
Yes, yes. Thank
Uh,
you so much. Tomorrow I'll discuss that biography-based optimization. I'm sorry I'm late, but we have started also late slightly.
sir.
Yeah.
So,
So no problem.
participants, now we will have a break and then the next session will be continued. Thank you. Dear participants, it is my pleasure to introduce you to our new speaker, Dr. Ila Sharma. She is my colleague in the Department of Electronics and Communication Engineering, MNIT Jaipur, as well as the coordinator of this particular program along with me. She is currently assistant professor in our department. She has received her BE degree from GEC Raipur in Electronics and Telecommunication Engineering and completed MTech from JUIT Solan and PhD from IIIT DM Jabalpur. She has published several research papers in peer-reviewed international journals and international conference proceedings and book chapters in Springers. Her academic research interests are multi-rate signal processing, multi-rate filter banks, optimization of digital filter design, swarm and evolutionary competition, neural networks, and artificial intelligence. She has got Best Paper Award in many international conferences held in India and abroad. She is a senior member of IEEE, also hold membership of IEEE Women in Engineering, IEEE Signal Processing Society, and IEEE Census Council. With this brief introduction, over to you, madam, for the talk today.
Thank you so much, sir, for this warm introduction to me. Let me check. Okay. Good evening, everyone. In this session, we are going to discuss this cuckoo search algorithm, in which we will be knowing what is this cuckoo search, the mathematical formation, followed by this optimization or this technique in filter designing. So let's begin with it. The concept of this cuckoo search was initially proposed by Yang and Deb in 2009. After that, they have proposed many integration to it for solving the various engineering problems, and they have improvised this, and after that we get different variant of it. So firstly, we'll know what is the basic of this cuckoo search. What does it mean? So let's start with it. Don't you think so? These cuckoos are fascinating birds, not only because of this beautiful sound, what they make, but also because of their unique reproduction strategy. That is the search, the cuckoo search, as its name indicates. So basically, they have two technology or the two methodology which is comprised in this search. First is brute parasitism that we are going to discuss, and second is Levy flight behavior. Both are the important thing, and we can say this cuckoo search algorithm is based on this two mechanisms. So let's talk about this search. Let's talk about their aggressive reproduction strategy. What is that? Have you ever thought cuckoo bird never built any nest for their egg? It is surprising, isn't it? So basically, these cuckoo birds intentionally lay their egg to other birds' nest that we call host nest, or we can say foster parents to their young cuckoo birds. This is called brute parasitism behavior. So intentionally, these species, cuckoo species, lay their egg to the other bird's host. Some of the species, some are the classification which I have listed here, that Annie and Guerra cuckoo lay their egg in communal nest through their, who they may remove others' eggs to increase the hatching probability of their eggs. Okay, there are the two way of doing that. We have classified here the Annie and Guerra cuckoo bird. What they do, they lay their eggs in the host nets and they remove others' host nets egg to increase the hatching probability so that their egg can be grown up. And the another kind of sub-classified species of this cuckoo bird, that is Tapera, that involved a unique a unique specialization for mimicry of these eggs color or the pattern, we can say. They mimic the egg colors and the pattern of host bulb nest so that the probability of eggs being abundant is raised and their reproductivity. This will be demonstrated clearly through this diagram, this representation. You can observe this is a host bird's nest. The blue one are host bird's egg. And the another one that is try to mimic this not so clearly, but that is the cuckoo egg. So now the question comes, what if the host net discover that this egg doesn't belong to my nest or doesn't belong to me? Then what happened? Yes, there is a conflict with this intruding cuckoos. That means if a host bird discovers that these eggs are not their own, so either they will throw it away. We can say this will be the alien eggs. That means the cuckoo bird eggs will be a alien eggs to that particular host net. So either they will throw or simply abandon its nest and they will build a new nest elsewhere. That is the mechanism. Okay. So always cuckoo bird try to mimicry these eggs and the host net always discovers or try to discover. If not, so if he will grow up or he will be as acting as a foster parent for that young cuckoo bird. I think this idea is clear now. So for governing this cuckoo search mechanism, whatever we have discussed, okay, this cuckoo bird searches for the nest and after that some host nest is discovered and after that he intentionally lay her egg to that particular nest. Okay, these are the criteria. This mechanism is mathematically formed to generalize this cuckoo search optimization algorithm. Along with one important point, that is Levy flight, that we are going to discuss soon. But still, what are the magic rules for this cuckoo search? There are three magic rules. Okay, basically three main principles how this cuckoo search are performed. First, each cuckoo lays one egg at a time and dumps it is in randomly chosen nest. That means searching of nest will be randomly. There will be lots of nests and it is randomly chosen by a cuckoo bird to lay at her egg. So the best nest with high quality of eggs will carry over to the next generation. Definitely among the other eggs, the best will be taken to carry out for next generation. And third, the number of available host nets is fixed and a host can discover an alien egg with probability of 0 to 1. That's the thing. That's the 3 points that should be remembered while designing this cuckoo search algorithm. So now the question comes, how we are going to that? What will be the mathematical formation of it? So each egg in a nest represents a solution. Listen to me very carefully. Each egg in a nest represents a solution and a cuckoo egg represents a new solution. So the aim is to use the new and potentially better solution, that is our cuckoos, to replace a not so good or other solution in the nest. Okay, we are making analogy, so they try to connect with it. So in the simplest form, we can say each nest has one egg, as the third magical rule says. Each nest has one egg. The algorithm can be extended to more complicated cases where we can consider multiple eggs representing a set of solutions. I think this is clear. In this way, we make an analogy. Okay. Nest size, then eggs representing solutions. Now I think now we are in the third day of this optimization FDP. So now you are getting that what is the solution, what we are talking about. So I think these are resumed, these are understandable. So now what was the Levy flight mechanism? Okay, in animals like fruit, bees, or we can say some animals, some fruit bees, some bee behavior, what they do, they randomly search for their food. And this is the random walk. So this is the Levy flight mechanism where we say this Levy flight mechanism because this is based on this Levy distribution, and name Levy itself is given by this French mathematician who developed this. Okay, so basically it demonstrates a walk, a random walk, searched by different animals, bees, and other insect or species for their food. Okay, and the important thing in this Levy flight is that this is a random walk. You can observe in this figure, these are the different points starting from first to end. This is the different path achieved by a different species, or you can consider, for example, it is by one species or one bee or other insects that they try to find their solution or try to find their food. Okay. So definitely it was discovered by Levy. So Levy flight based on the Levy distribution, and if it is, we are talking about the distribution, definitely there will be some probability and there should be some index associated with it. Okay, so that thing we will also discuss. So this is the general governing equation for demonstrating this Levy flight mechanism. So whenever we generate a new solution that is represented by this equation, you can observe it is also mentioned in this boxes, the new solutions, then the current solution, then the Levy flight. Okay, here alpha that is associated with this step size generally taken greater than 0, or in general cases when you tune it for the particular application, it can be taken as 1 or other. You can observe or you can examine other examples on it, and after that you tune it. So generally it is taken at 1 and it should be greater than 0. So till now we have known that CS algorithm, that is the cuckoo search algorithm, searching for nest so that the best solution can be generated. Okay, so each egg in a nest symbolizes a possible result, and cuckoo egg symbolize a newly generated result. So what is our task? Now we are going to mathematically formulate it. So our task is to pay more weightage to newly generated and better solution to substitute the poor solution in the nest. Okay, and in every optimization problem, there is some cost function or mathematically formed objective function where we minimize or maximize it as per our requirement. Isn't it so? You have been seeing different optimization algorithm. We are also discussing it. So there is a cost function, objective function f of x, and that has to be maximized or minimized according to our problem, given problem. So whatever I have said just about this cuckoo search, their brood parasitic behavior and the Levy flight, that can be demonstrated through this pseudocode also. So just observe line by line. Firstly, we define our objective function, whatever it may be, depending on the problem to problem in the different field, different engineering field. Then we initialize this population. In our case, we have a host nest represented at n, and we have different solution representing by xi. Don't worry, it will be cleared out in the next slides. Just go through this pseudocode. Why it is demonstrated here. We have put up condition accordingly. We have to define certain tolerance or maximum generation or the iteration or the stopping criteria. See, make an analogy with this algorithm. That was the theory, and we have to formulate it for particular application. So how will do it? How will making this loops? How will this? So pseudocode is there. Just try to understand it. So we'll put up one condition here. While our iteration is less than maximum generation or a stopping criteria. So get a cuckoo randomly by this Levy flight, evaluate the fitness function, and accordingly choose the nest. Then again, what we do in this optimization technique, we compare the previous solution and the current solution, and we check whether which one is better. If previous one is better, so we leave the current solution. If current is better, we leave the previous and we tell that this is the best solution. Okay. In a similar fashion, these conditions are checked, these objective functions are solutions are checked, and accordingly this is acted. Okay. One important thing with this cuckoo search is this probability of abundance. Or in Levy flight, we have that the discoverable probability. You can observe here, this is a PA. Okay, that is the probability how the host nest can discover whether the particular egg is belong to her or not. That is the probability of discovery, PA, generally given in the value 0 to 1, and in most of the problem it is generally kept as 0.25. Okay, I have also mentioned this parameter so that if you want to optimize any problem, so initial judgment of this sizes should be known. So that we will also discuss. Let's begin with this formulation. How we will formulate? It may be classified into 4 stages. First is your solution initialization. Second is your modification of search space. Third, sorting of the best solution. And fourth, exploration of poor solution. Our case it is nest using random walk, or we can say using Levy flight. So let's discuss solution initialization. Okay, see, we have mathematically formulated this. So there may be some equation generating or representing our methodology. So this is the equation how we initialize our cuckoo search algorithm. You can observe this equation where I, that is our size. Definitely there will be some upper and lower limit depending on the case or depending on the objective function. You define your upper and lower boundaries. And this is n is your search space matrix, and in search space matrix each solution that is defined in a randomly generated value, we can say this is our dimension d. So in this way we formulate our search space matrix. Okay, we define our nest, we initialize our values with upper and lower limit bound through this governing equation in randomly generated manner in d-dimensional space. Okay, and here I correspond to the index which is useful for optimizing or computation of this objective function. Okay. Modification of search space. Okay, now you have generated the solution. Now accordingly you have to modify this solution whenever the Levy flight mechanism is needed, or you generate any solution. So this is the equation for modification of search space. Okay, here this equation, this n and I represent the new solution, or we can say the solution representing by a cuckoo hen. Okay, in a random fashion. So here Levy flight is used. This is the generalized form, or we can say generalized equation governing this Levy flight mechanism. So this is generally associated with the how this path is associating how this species is traveling for achieving a solution. Now, sorting of best solution. Till now, you have generated the solution. You have firstly initializes your nest. Then you have generated the solution, and now sorting of the best solution. Okay. Now the thing is, you have your objective function for computing the difference or the error or any of that for achieving maximum value or the minimum value, where you put your parameter of optimization and you get the solutions. So the thing is how you will sort it, how you will find your best value. In many of the optimization algorithm like your PSO, you have been gone through this local best or the global best one. Similarly, in the cases like where we compute this fitness function for this evaluation, what we do is simply compute the fitness according to each of the nest. Okay, corresponding to each of nest, every fitness function is computed, and again they are compared with the previous one. Just like in the equation you can observe, just go through it. Here n and I represent the new solution, and this ni represent the previous solution. So just the case, you can observe the final solution will be what? The fitness function corresponding to each of nest will be computed, and they will be compared one by one. Okay. So if there is a n-dimensional, okay, we can simplify it. We can go to a single dimension. Suppose you have 100 element, you want to optimize it. So each of the element, or we can say these are the nest size is your 100 cross 1 for a single dimensional problem. You can go for multiple one also. Accordingly, your search space will be governed. Okay, so come back to the point. If you are having 100 points and you want to optimize a certain function like your sinusoidal one or any equations you want to pick the minima or maxima of it, and suppose your parameter of optimization is x. Okay, so this x is representing, just make an analogy how these things are governing. So this x represent this nest. Okay, so each of the time we put a single value to our fitness function and the particular solution will be computed. And again, it will be compared. And that which is having the best solution, corresponding value will be our optimum one. Okay, we'll see also some application in this filter designing, so the idea will be more clear to you. So let's come back to our sorting of best solution. So here in this way, these are the governing equation from which we compare the fitness value and we assign the best solution to it. So the solution which is updated according to this comparison, we select what the best solution among the 100 present solutions, and accordingly we iterate it. As per your given iteration, we iterate it. See, these formulas are very important. These are mathematically formed. You have to go through it. You design your optimization problem to solve these other objective functions. So here you can observe the best value has been chosen as maximum of fitness function. This Ni is your nest. You can observe here. Okay. And the best solution is Nk corresponding to that fitness value from which we get the maximum value of this. Getting my point? How these things are happening. So now we get Nk, that is a solution for which maximum fitness is measured among all the possible solutions in our search space. Okay, so this can be multi-dimensional also. This can be single dimensional also. So according to or from your problem to problem, engineering problems, this can be modeled. Now the exploration of poor solution. This is the particular case of this cuckoo search, where if a host has discovered, so what he will do, either he will abandon that particular nest, okay, or it will be discarded. We say this is discarded. So depending on the probability of discovery, that is our PA, which I was talking about, that it should be in between 0 to 1. So according to which it is defined, but it also affect our convergence or speed in our optimization algorithm. Okay, if it is low, then the system will act low, and if it is high, the system will act high. So it directly depends the convergence speed or the governing speed of our optimization algorithm. So as I said, the tuning of this parameter is very important as the different optimization algorithms. Okay, this is how this exploration is done for the poor solution. Okay, this is the formula. The first one, as I said, it directly affects. So if value is too small, then the algorithm's speed will be small, but the exploration will be deeper. So you have to choose this nicely, and you have to make it some trade-off in between. So what is the more prior to you? So you have to do something, some trade-off in which. Okay. Here in the equation, you can observe Ni is our best solution, but this Nd and Nd bar are now row vectors that contains random permutation of these integers in the range 0 to 1. And the Ki is given by this, where your P alpha is probability of discovery. Okay. Okay. Let's go to the flow chart. Till now, we have observed some mathematical formulation of it. Okay, by using this equation, we can easily form our problem. We can define our objective function. So let's summarize it, how these things are happening. Let's summarize it briefly with this flow chart. So firstly, you have to initialize the population of n host nest xi. Okay, And then we have to get cuckoo birds, that is randomly generated by Levy flight, index are I. And now we have to evaluate the fitness function. So we have initialized these parameters, we have governed, we have formulated some objective function for minimization or maximization of it. And after that, we evaluate the fitness function. Okay. Then we select the nest among the n randomly generated. We have our search space, one by one, we compute this fitness function. So suppose that example, first nest has computed and you have taken out for evaluating this fitness function. And now the second one is computed and now you will compare it just like in this flow chart. Go through it. Okay. Fi is less than or equal to Fj. If yes, then you replace J by the new solution. Here J is indicating your new solution. Okay. And if not, then let J as a solution. You go back to this. Okay. Abandon the fraction. Depending on the value of P alpha, this will be either abundant or that will be discarded. If so, if it is better, then you keep the current best. You stop the criteria. If not, you again go back to generation of this cuckoo bird. Okay, so the thing is to find best solution corresponding to optimized objective function. So why we are discussing this means what is the importance of this cuckoo search algorithm? First thing till now, the simplicity means in this algorithm you have to find a single parameter that is your best nest, isn't it so? So it makes this algorithm very easy to implement. So now after comparison with different mathematical algorithm of the optimization algorithm such as PSO and the harmony search, so cuckoo search has been indulged as a very simple and important optimization algorithm, easy to implement. And also the convergence is also improved. Not only this is the basics of this cuckoo search, after that the hybridization of it, that means hybrid version with the PSO and the other algorithm associated with this in the different spaces or the different stages of this algorithm, like for how the probability will be selected for discarding, how the new solutions are generated, if we want to generate it randomly or pre-specified, how it will be generating. So in this way, the things goes on. As I said, it was initially given by in 2009. So after that, many modifications with improve and many variant of this cuckoo search have been associated. These are the some advantages of this cuckoo search. Just it deals with the multi-criteria optimization problem. That means you have so many criteria you put on for optimizing one objective function. You can use this cuckoo search there. Definitely simplicity and easy to implement. The concept, the methodology is same to find or to search a best net, isn't it? And it can be still hybridized. As I said, different swarm-based optimization can be hybridized with it, combined with it, so that it can be come up with a improved cuckoo search. And also the convergence speed, which is depending on our probability, can be speed up. So there are a variety of applications for this cuckoo search that can be used for different applications or different engineering problems. Just like some of these I have listed here: design optimization of filter, engineering optimization, antenna wave propagation, reliability problems, stability analysis, and many more. Okay, so let's discuss one of them. I will be concentrated on this optimization of filter or designing of this filter part. So firstly, I assume you all know about this digital filter, but some of the brief information should be noted so it will be helpful for designing these filters, isn't it so? So this designing filter, as everybody knows, that filter are something that it passes some of the frequencies and it stops some of the frequencies. So accordingly, if it is passing lower range frequency, we have classified into low pass, high pass, band stop filter, and according to its impulse response, they are again classified as a FIR filter, finite impulse response filter, then infinite impulse response filter. So Basically, filters are classified in these types. And what is the main motto of optimization of this digital filter? So digital filter generally associated with their frequency responses. Okay. So that should be improved. And it should not be graded, or suppose if you computed some elements or you computed some indexes over there, so that should not degrade our overall performance. So let's begin it. Let's start. Firstly, we'll see what are the filters, how they are designed, and how it can be designed using the Scopus search optimization. Okay. So as I said, filter is a system that is associated with some mathematical operations and that passes certain range of frequencies and rejects other range of frequencies as per our application. So again, it has two types, finite and infinite impulse response filter. So in a FIR filter, I will abbreviate it as FIR and IIR. So in FIR filter, which have finite series of impulse response. Similarly, for IIR filter, we have infinite impulse response. Okay, this is a simple block diagram associated with the filter response or the impulse response of that particular filter. Okay, so in filter designing, what is our main objective? Our objective to that the transfer function, or we can say here the filter's response. The transfer function, transfer function output by input. So the transfer function that should be realizable, and that is approximating a given frequency response for a particular specification. Like you want to have or you want to pass a certain amplitude or certain signal from 10 hertz to 20 hertz. So you want to reject whatever information or whatever noise that is added up in your proper information. So you want to filter it out. What does it mean? You want to reject all the components or all the amplitude that is in between 0 to 10 hertz or after 20 hertz. Okay, so you need to have some kind of filter there. So that is the thing, that is the approximation of this magnitude response and this frequency response. So that is needed, that is the main objective of this filter designing. So either magnitude, either frequency, either the phase that should be specified for a particular design that should be optimized. Okay. As we are discussing, there are four basic types of ideal filters. Apart from this FIR and IIR, again, these filters, low pass, high pass, band pass, and band stop, that can be designed. Okay, that can be designed by using both IIR and FIR filters. So don't get confused with it. These are same. But the thing is, FIR is finite impulse response and IIR is infinite one. But these filters can be designed. So generally in practice, as we were discussing, that this magnitude response or the specification which was given to a particular filter to different application or the different requirement, that should be approximated. Okay, the magnitude response, for example, let's suppose we want to optimize or we want to approximate the magnitude response of that particular filter. So what you will do, how you will optimize? Because ideally it should be a flat response, just like here. See, observe the first one, the first figure where the low pass filter is indicating. So ideally, in an ideal filter, that should be of flat response. You observe the transition region is also very sharp, but practically it is like that. You can observe some ripples here in the pass band region and some ripples in the stop band region. And also our transition region is a steep kind of thing. So this is a practical filter, but we want to idealize one. What does it mean? Instead of this ripple, we want flat magnitude response. Instead of this steep transition band, we want sharp transition band. Instead of ripples in the stop band, we want flat. So these are the constraints, these are the things. And this is your motto. So you need to have those filter coefficients that have the flat magnitude response in the pass band region. Okay, zero magnitude response in the stop band region. Okay, and the transition band should be star. Accordingly, you have to model some objective function so that this criteria, this aim can be achieved. Okay, for simplicity, I just tell you what is this thing. This del P is your passband ripples. That means ripples associated in the passband regions. And this del S is your stopband ripples associated with this. This omega P and omega S your passband and stopband frequencies. And this mod of G, E, J, omega is your magnitude response. Okay. So let's suppose, as I said, what do you want to have? You want to have this magnitude response as flat as possible in the passband region, and in the stopband region, the magnitude response should be 0, isn't it? So these are mathematically written over here. You just observe this G e to the power j omega in mod is representing your passband region's magnitude. That is should be in between this. Okay, I will again go back to this previous slide so that you can observe what I am writing here. Okay, this G e j omega. So that is in between 1 minus del P to 1 plus del P, as like in this figure in the passband region, and how it is defined in the stopband region. That is the way. Okay. So these are the specification. Omega P, omega S that we have already discussed. Okay, one cutoff frequency. Generally, the cutoff frequency is computed as the WP plus WS divided by 2. That we add WP, passband and stopband frequency, and we divide it by 2, and we compute this cutoff frequency. After that, we have different standardization of computing it, because according to given specification, like if passband ripple or stopband ripple are given, or the attenuations are given, or the frequency ranges are given, or if magnitude response is given, then you have to compute other things. So depending on the specification, we compute each and every element. So generally, these are specifications which are given, or we can compute the peak passband ripple. So if any of the values are given, we can compute another one. And also, if you have designed any filter, you have coefficients, so you have to measure this different values associated with it. Okay. Performance parameter, performance measuring parameters. So I know this is somehow some del P, del S, but if you go through a slide again, when it is shared, then you will be knowing, okay, this is corresponding to this. So this is the required specification to know about this filter. So the transfer function, which we have defined, suppose this is h of z. So the frequency response specification or the requirement of every application is given to us. Now we have to define, or we have to design a filter that is stable and which should have a low complexity or low computational complexity. Okay, so we have two variety. We can do it with IIR filter, we can do it with FIR filter. But again, it has several advantages, disadvantages. So for simplicity, in today's lecture, I will be discussing the FIR filter. But for information purpose, you can observe this transfer function equation that is for IIR digital filter. Okay, both poles and zeros are there. And let's discuss this FIR filter that we are going to design using this cuckoo search algorithm. So for FIR digital filter, the FIR transfer function is given by this formula. Okay. And for reducing computational complexity, this order should be very less. Generally, we take different examples of it like order of 10, 20, 30, 40, and we generate the solutions, we get the different values, we compute the performance evaluation parameter, and after that we decide, okay, this much of order is needed. But see, the computational complexity is also increases, the complexity of the system is also increased as we increase the number of order or degree of order. So that is also important. That is the another issue that should be optimized. So this designing of FIR filter can be accomplished into two distinguished approach. First is your conventional one. where we initially put a translation of any analog filter. We define analog filter, then we transfer it or we translate into a digital domain. I think you can recall your Butterworth, Chevashi, Vittigal based different filters. So that was the analog filter, then you translate into digital one. Again, the complexity increases and the lots of error arises, some like quantization error for this convergence. Okay. And the second method is optimization based approach. So you can formulate some design problem and the computer aided design we can use to optimize it so that this digital filter can be directly designed. Okay. So our aim is or our approach is the second one, optimization based approach, where we govern some objective function and then we want to minimize or maximize it according to our formulated objective function. So let's begin with it. As I said in the previous slide when we were discussing, okay, we want to approximate the magnitude response. You want to have suppose let's consider you are designing a low pass filter. Okay, so ideally the low pass should be the flat magnitude response in the pass band region and the zero magnitude response in the stop band region and sharp transition band. So for a given example, suppose you are computing your magnitude response. So here you can observe this h of ej omega subscript with I. This is representing your ideal magnitude response. And next h of ej omega, that is subscript with d, is your design filters response or design filter magnitude response. So ideally for any low pass filter, what should be the magnitude response? Can you guess? That is 1. If you are defining suppose 0 to 1 and this frequency is suppose 0 to pi or 2 pi, whatever you are taking, or if you are taking in a digital domain, so you digitize it, the frequency range will be in 0 to 1. So we are talking about this magnitude response. So ideally the response should be 1. Okay, so we try to approximate our magnitude or those coefficient that is near to our ideal one. So each of the time we'll compute our magnitude response, we compare it with our ideal one, and we'll get the value of objective function and the function, which is the minimum value of it after comparison. Suppose you have compared, you have taken 5 set of coefficient. For first set of coefficient, you have computed your magnitude response. For second set of coefficient, you have again computed magnitude response. In this way, you have 5 magnitude responses. You compare those 5 magnitude responses here from the ideal one, you will get some minimum value of it associated with fx1, fx2, 3, 4, and 5. And again, the whatever value that is the minimum one. Okay, so that corresponding design filter response coefficients will be optimum one. Getting my point, how this objective function is formulated here. We want to approximate magnitudes, approximate the magnitude response. So we will compare with it ideal one and we'll try to minimize this function. So the people think about the problem associated with this different engineering design problems, what they want to achieve, what are their aims, and accordingly they formulate some objective function. In our case, while designing this FIR low pass filter, this is our objective function. Okay, so this is the simplest one. Again, people can put different condition here. And again, it can be modeled as the multi-objective function. We have 2-3 objectives like the constraint which we have discussed. Okay, the pass band ripple should be this much, the stop band ripple should be this much, this value, frequency value should be in this range. So accordingly, this can be designed or this can be modified. So we'll start with the simple one. We compute this filter coefficients and we compare with this and we formulate this. We will govern this objective function. I think idea of objective function is clear. Why I have created this only. Okay, moving ahead. So now these are the steps. So guys, now you have to make analogy. Okay, recall the cuckoo search algorithm and make an analogy how the cuckoo search optimization is utilizing in this optimization or in this designing of filter. So firstly, we will initialize everything. So you can go to the step 1, specify the design specification, including the filters design specification, stop band attenuation, order of filter, passband and stop band frequencies. And the second step to design the parameter of our optimization algorithm, that is our cuckoo search, number of post nest, probability of action, or step size and iterations. You can also initialize the tolerance. Okay. Now the step 3, set the parameter for optimization algorithm. So firstly, according to our first equation, okay, so you will initialize the nest. We will generate our search space represented as AI of t, and we define our iteration. Okay, so each nest correspond to the different value of cutoff frequency. Here, the parameter of optimization is cutoff frequency. Why I have taken? Okay. My search space, if I want to have 10 number of nests, okay, and my single optimization parameter is there. So what will be my search space? 10 cross 1 dimension. And if I suppose want to optimize so many parameter of optimization, suppose I want to optimize 4 parameter associated with my filters. So what will be the search dimension? 10 cross 4. So for simplicity, I have taken only single parameter of optimization for this filter, and in this way we will govern our search space. Okay, so that's why the nest corresponding to different value of cutoff frequency. So what is the main thing? We have set of cutoff frequency. We will put it into our cuckoo search algorithm. Each time with each of the nest, from the first nest, will govern our objective function. We generate, we initialize the solution. Accordingly, the whatever value of our objective function, that will be recorded. Then the second nest corresponding solution, the third, then fourth. And in this way, they will compare according to our function, previous to next solution, and finally we get that. Okay, we'll go step by step. Don't confuse with it. So the nest correspond to the different value of this cutoff frequency that is randomly generated. And here, because of filter, we are now optimizing the cutoff frequency. And if you remember, I told you that this cutoff frequency is generally taken as passband frequency plus stop band frequency division by 2. So accordingly, we can set up a range that passband frequency should be your lower and stop band frequency should be of your lower and the passband will be your upper bound. Or you can take also the values as 0 and 1. Why I have taken 0 and 1 as my upper and lower bound? Because I have digitally demonstrated my frequencies. Okay, that can be in 0 to pi. And I told you, if you're designing a digital frequency, a digital filter, you can take it into 0 to 1. So definitely my lower bound should be 0 and my higher bound would be 1. So here the cutoff frequency I am utilizing or optimizing. So my lower and upper bound I have defined accordingly. You can take 0 and 1 in place of this also. So now the next step, check whether generated cuckoos are in bound, whether it is in this frequency range. If yes, you can proceed to another step. That means you can calculate the coefficient of prototype filter. Then when this prototype filter's coefficients are computed based on this cutoff frequencies, based on this filter has been designed, we compute the coefficients. Now we evaluate the fitness function that is represented as phi here for each value of AIT that we have discussed here. That is AIT, that is our solutions. So for each value of this, we will compute this fitness function. Now the new solution, or the, if you can recall, that is our cuckoo bird. So new solutions can be generated by this as represented as AIT plus 1 for this cuckoo by utilizing that Levy flight mechanism. Okay, and accordingly the fitness value can be computed. So you can observe this psi AIT plus 1 representing a fitness value corresponding to our new solution. Now we'll compare. Okay, just observe carefully step 7. Now we'll compare the better solution, or we can say we compare the previous solution to our current solution. Okay, if it is better than the previous one, so we'll take it as a best solution. If it is not, we again generate the solution, we again go to the next nest value and again compute the fitness function and then again compare. And so as our algorithm works, just like our flowchart and pseudocode. Now again, suppose you have taken only one iteration at a time. Only one time you have checking all these things. So you can take the iteration 10, 100, whatever you want to have, depending on the convergence time. If it is converging in a meantime, suppose in the matter of iteration of 20, 30, you can observe it. So you can stop there. You can put your stopping criteria according to it. But every time, if you are governing any algorithm, you have to check its convergence. Okay, how it is converging, how the value is achieving, when we are getting the optimum solutions. So check whether the stopping criteria has been met or not, or whether the program has reached to its maximum number of iteration. Then you can terminate the program, or you can again go back to the step 5, where we evaluate the fitness function for different nest values. And again, you have to compute this fitness and then comparison, then corresponding best solution. Thing is, these are the parameters which I have taken for designing this filter. So what it has done, the initialization of this nest with the corresponding parameter of optimization in case of filter, that is our cutoff frequency, has been done. Okay, that is randomly generated solution. The proposed formulated objective function has been taken account, where from given each of the cutoff frequency, the magnitude response is computed, then again compared with the ideal one, and corresponding value, the difference value has been noted as a solution. Then the next cutoff frequency value has been taken, put up to the computation of this magnitude response of filter, again compared with the ideal one, and the difference value is noted, and so on. And which one is the minimum one, that will be considered as optimum solution, and corresponding cutoff frequency will be considered as optimized cutoff frequency. Okay. So in our case, while designing this filter using this cuckoo search algorithm, the population size is taken as 50, the discovery rate has been taken as 0.25, and iteration has been taken as 100. So this fidelity parameter is also tested here. The selection of parameter accordingly. You can observe one object, the convergence of this function, objective function, with respect to nest size, and the convergence of this objective function with respect to this number of iteration is performed. So you can observe that if the nest size is taken as 50, okay, this is a minima problem. Okay, we are taking the minimization of particular objective function. So don't confuse with it. In the minimization, the graph always draw downside. In the maximization, the graph always draw upside. I think that was clear in the last day's lectures too. Okay, so you can observe here how your objective function is converges. So here you can observe in the figure B, after 40 to 50 number of iteration, somehow our objective function is converging. Okay. Similarly here, if we take a nest size up to 40, so after that our objective function is converging. Okay. So you can check this convergence, and accordingly you can plan to put these values in your algorithm. So here the different low pass filter, high pass filter, and band pass, these filters have been designed. This specifically I have taken for this low pass filter. You can observe here the different filter length has been taken, like 21, 31, 41, 51. Don't confuse with it this numbering, because filter length is generally what? Filter order plus 1. So your order are 20, 30, 40, and 50. So for ease, I have demonstrated this much filter design only. So the given passband ripples and the given stop band ripples and the stop band attenuations are listed here. See, this is based on your design problem. Okay, what you are designing. Accordingly, you have to choose this parameter. Some of the parameters can be given, some of the parameters you have to compute through different formulas. But the thing is, You can design each and every problem using this optimization if you have a better cost function. So important is that how the objective function is formulated. You have put the different constraint on it or not. This is the what magnitude response of this particular design has been computed. You can observe, try to have the flat response in the passband region. This one, I don't know whether you can see my arrow or not. So here you can observe almost flat response has been observed at 0.4. After some of the little bit ripples are there, and after that this is your stop band region. So somehow it has tried. Similarly for high pass filter, similarly for band pass filter, and similarly for band reject filter. So according to your design, so it was the simplest objective function. Now you can put different constraint of it, like your passband ripple should be in 0.01 to 0.001, whatever you want to put it on. So as much as precise you define or you design your filter, the response you get the maximum value or the ideal values or required values. So this is the magnitude response of different filters. So I want to again summarize this thing. This one. So the main idea was here to formulate or to get the better magnitude response, which we have calculated depending on the different cutoff frequency. Okay, you can directly take the filter coefficients too. Like here, our parameter of optimization was single, the cutoff frequency. Instead of that, you can directly put a set of coefficients there. For example, suppose you have taken 16 order filter. Okay, 16 order filter, how many coefficients you will be having? Including A naught. So you will be having 17. And if suppose this is a symmetric filter, so you can reduce it to half. So optimizing parameter should be half. So here the initial set, suppose you have taken the 10 nest. Okay, and your coefficients are of how much of word length? That word length is also important. So you can define it also. And suppose you have 8 filter coefficient to optimize. So your dimension will be your 10 cross 8. Now, instead of a single nest or the single cutoff frequency, now you will take 8 coefficient set and you will compute the magnitude response corresponding to it. Then you put this value to this objective function. Okay, and you compute this solution. Again, the second set of filter coefficient will be taken out. The response of this corresponding filter coefficient's magnitude will be computed, then compared, then the value, the minimum value associated with it will be recorded. Then again, third, fourth, up to 10 times. Okay, and again, the checking criteria for the best solution. Here in our case, the minimum value or minimum difference value will be taken out as our best solution or the optimized one. So the minimum value for this particular function, apart from all these 10 contexts, whatever you are getting, that will be corresponding to your optimum solution. And corresponding set of filter coefficient will be your optimized one. Okay, and you can design further. You can use or you can measure all the parameters associated with it, like errors, mean square error, passband error, stop band error. The performance evaluation parameters can be computed. So according to it, this can be multi-dimensional, single-dimensional. The constraint optimization, this is based on your objective function formulation. Okay, this parameter is dedicatedly set it for this filter designing. After being observation like this conversion in this one, if you are designing any problem, if you want to solve any optimization problem in any of the field, firstly go through the what you want to optimize, what is your aim, transform into a mathematical formulation like this equation. Like here in my case, I try to compute the magnitude response difference. Okay, the realized one to the ideal one. Similar fashion, you have to take a particular parameter of optimization or the different parameter of optimization. You check all of these things like objective function with respect to nest size, the objective function with respect to the iterations, how these parameters are converging. Accordingly, you put these values. Okay, and currently many improve cuckoo search optimization or the hybrid optimization has been taken in consideration for deciding this discovery rate and for designing this nest population sizes, random generation solution size. So in this way, you can design it. So this idea can be made towards for other filter bank designing or in the multi-rate signal processing, in the ECG signal compression, or in the wave propagation, where you want to optimize any frequency or any parameter, so you can keep in a track in this way. So these are the references, the first one and the second one. These are the modification, little bit of modification of this cuckoo. So till now, I want to end my presentation. If you have any query or question, you can ask me in the chat box. So any questions? Okay, let's take a 5 minutes break. After that, our lab session will be start. Thank you.
Hello participants. So hope you have enjoyed today's theory sessions, and like yesterday I have explained you and demonstrated you the genetic algorithm code in MATLAB. Today we are going to discuss about the codes of particle swarm optimization and differential evolution, two algorithms. Okay. So let's start with the particle swarm optimization. So in this particular algorithm, first we need to understand that genetic algorithm is a binary coded algorithm, whereas particle swarm optimization is a real coded algorithm. The difference between them is in binary coding, we always start with binary operators, that is 1010. In this particular manner, the populations get initialized. Okay. The problem with that is to evaluate the fitness function, always we need to convert this binary number into decimal number, then decimal number into its corresponding range, and then solve the fitness function. Every fitness function is defined within a particular limit. That means the optimization task you have to carry out within certain limit. You cannot take the bound as minus infinite to infinite. So you have to bring it to that particular range, like sin x maximization problem, then it is between 0 to 2 pi. If it is any other particular problem, then its corresponding bound you need to define. So the binary numbers which we have taken, that has to be converted into the decimal number and bring out to that bounded range to solve that particular problem. That is always with any of the binary based coding. Whereas in real number based coding, you can directly generate the solutions within that particular range and take the fitness evaluation. So the advantage is that you do not have to do this conversion again and again. Thereby you can save the computational complexity. So that's why compared to the binary genetic algorithm, the particle swarm optimization algorithm computational complexity is lower, or the algorithm runs faster manner compared to GA. So let's discuss about how we can generate the initial population. Over here, the population comprise of a number of particles. Okay. So I am not changing the problem. I am considering the same problem, sin x, either maximization or minimization between 0 to 2 pi. Okay. So for the same problem, how to solve it with this particle swarm optimization. So here I am defining, suppose P as vector of for my particles. Suppose we are considering 10 particles, then the particles can be defined by two things. One is their position as well as their velocities. Okay. So we have to define two things, particles position and particles velocity. So suppose the positions are defined by x1, x2, and x10. 10 thing representing the position, and then 10 thing representing the velocities. That is v1, v2 up to v10. These are the corresponding velocities. How I will initialize this velocity? That is sine of x and that value is range is between 0 to 2 pi. So you have to consider these x values between 0 to 2 pi. So if you are taking random number R, A, and D, random number, that will generate a random number in the range 0 to 1. In order to make it this particular range, then you have to multiply it with 2 pi. So 2 pi multiplied with a random number will generate this particular value directly. So 10 values of the thing we are considering, that suppose it is like 0.35, 0.46, and like 2.36, like that. Any value between 0 to 2 pi, that means 0 to 3.14 into 2, 6.28. Between 0 to 6.28, these values should lie. These values, these are all 10 values. Now their velocities. Velocities can be positive, can be negative. Okay. So these values are taken random numbers, and they can be negative as well as positive. So if we are considering any random number that is lying between 0 to 1. So if we wish negative values, then and minus 0.5. That will generate numbers between minus 0.5 to 0.5. So both in negative as well as positive direction, you can generate the velocities. So velocities can be minus 0.3, then 0.2, and 0.7, like that. It can be both negative and positive. This is what the initialization of particles, positions, and velocities. Okay. So once we have done this particular process, then our objective is to calculate the best particle, which will lead our entire thing. Okay. And that particular thing we call it as global best particle, G best particle, which is best among all these values. So which one is best, that you can able to determine by calculating the fitness function. So these particles positions will be fed in the fitness function f dot, and we will obtain the resultant value, that is sine of this x1, sine of x2, and all these values, sine of x2. Among these values, which one is the highest values? So these do have certain values. So which one is highest? Suppose I am saying that this x7, sine of x7, this is highest. Then its corresponding position. What is its corresponding position? The seventh position over here. Seventh position is particles global best position. This is global best particle, and this is the global best position. I hope it is clear to everybody that which is giving the highest value, if it is a maximization problem, or which is giving the lowest value, that is the global best position. Okay, based upon the maximization or minimization problem. Okay, suppose the seventh one. Okay, now we need to consider the local best particle, because in the update equation you need two things. One is local best, another one is global best. You understood about the global best. Now talk about the local best. When you are starting your search, at that time you do not have any previous records available. So that's why initially for the first iteration when you are starting, your local best is equal to G best. Sorry, local best is equal to your present position. The present position is equal to P. So local best is equal to the position where you are starting. So what is local best? Each individual particle's own best position is local best. So local best is equal to P initially. So every particle has its own best position. Okay. Now for updating the equation, you will do the update by velocity update. These velocities, they will be updated. V is equal to some weight into the previous velocities, that is V plus C1 R1. These C1 and R1 both are constant values. Okay, and the global best G best minus the present position, that is P. G best, you understand, it is always a single value. Which is the best position? That is the seventh one is the best position. That is always a single value. And present position is always a vector. This is always a vector. You observe that 10 values are there. So from this single value, you have to subtract this 10 values, the vector values. So from one unit to every unit you need to subtract in this particular. Then plus C2 R2 into L best minus P. L best is initially L best and P, both the things are same. So this particular term will become equal to 0 for the first iteration. And the velocity update will happen because of the weight factor. W is a value that can be taken as a constant value, or that value will reduce with respect to time. Okay, and like this it will go on updating, and once the velocity is updated, then the particle position x will be updated, is equal to x plus. So this is what we are going to observe in this particular algorithm. Then once this velocity got updated, then how to calculate the local best and the global best, that you need to understand. Okay. So now let's have a look at its code, and then further we will come for the discussion. I hope it is visible. This is the code of the particle swarm optimization, and you know about this tick-tock operation now from the genetic algorithm. Now over here, I told you that we need to consider the lower and the upper bound of the variable. So the lower bound is taken as 0, upper bound of the variable is taken as 2 pi. I have already explained to you. Then the PSO parameter values. Okay. So population size, that how many number of population we are considering, they are taken as 10. This weight value W, that is varying from 0.9 to 0.4. Okay. Initially, when you are taking this W value is taken higher value, so that the particles will freely search in the entire space, and gradually with respect to the increase in iteration, the W value decreases. 0.9 is the highest value, 0.4 is the lowest value. So it will slowly decrease from 0.9 to 0.4 value. Then the other constants like C1 and C2, they are acceleration constants. Their values are taken as 2, 2. C1 and C2, both values are taken 2, 2. Maximum iteration is taken as 100. And maximum run, repeated runs of the algorithm we use to perform, because the algorithm does not give same solution. So that's why maximum run we have taken it as 10. So for this, what we are going to do, we are going to generate the initial population. I told you that we have to generate it within a specific range. So for here, we have taken this is the generation of the particle, initial position, okay, x0, and that is generated by this lower bound, that is 0, plus random number into upper bound minus lower bound. So within that, it has been generated, and once we can execute it, you can able to observe that the x0 value, so you observe the values have been generated between 0 to 2 pi. Okay, so 0 to 2 pi, that is 6.28. Within that, these values have been generated, and their values have been taken the round of values. Now the initial population we are considering, and then the velocities have been taken. Either you can take it positive, negative, both, or you can take it positive. There is no problem with it. So over here, a 0.1 into that original velocity has been taken as the initial velocity. All velocities, it is, once I have attended the lecture in IEEE CEC, where they are saying that when the particles are initially starting, that is by Eberhard. So they are saying that once the particles are starting at the initial stage, the particles try to move in one direction. They do not always think that I should move in opposite direction. Okay. So initially the particle velocity, they are always taken as positive. And with respect to the time, they may become positive, negative, because the bars can move in forward direction as well as in reverse direction. But whenever they are starting, always the start is in one direction, means any particular direction they start, and their velocity is initially taken as positive entity. So that's why over here, this is 0.1 into the position is taken as velocity. Then the initial position, its corresponding fitness value has been calculated, that is sign value for all 10 particles. N is taken as 10. So in the F0, we have calculated the signs fitness value. Then here the objective is to minimize the thing for sin x. To determine, the objective of the problem is to determine the minimum value of sin x in the range 0 to 2 pi. So we have to consider the function minimum value. Okay. So over here, I have taken found out the fitness value of sine. Okay, then minimum of f0, that is minimum of f0 will give my global best value, that which is the minimum among all. So the minimum value and its corresponding number I have stored over here. F mean 0 is the minimum fitness value and its corresponding index I have stored in index 0. Okay. Now I told you that initial P best is the present position of the particle, because the particle has not yet started flying. Okay, so we do not have any past experience to compare. So that's why initial P best is equal to the present position or initial position of the particle. So P best is equal to x0, what I have explained. Initial position is taken x0, so P best is equal to x0. Now global best is a single value, which is the minimum value of the problem. So what is the minimum value? The minimum value we have calculated, that f means 0 and corresponding index is index 0. So where this particular thing is, so x0's index 0, that is giving us the global best. So global best is the single best position which is corresponding to the minimum value. So x0's index 0 is giving us the global best position. Now we need to start the iteration of the algorithm. The algorithm will, this is the initial condition, that initial position we have defined, initial velocity we have defined, initial global best we have defined, and initial local best we have defined. Now we have to update the particle positions in all over the space. Okay, so the particle positions will be updated based upon a tolerance. So we are considering either the algorithm we need to stop, either it reaches to maximum iteration. The maximum iteration we have defined as 100 number of iteration. You observe that maximum iteration is 100, or we are defining a tolerance, that either it has to satisfy this condition less than maximum iteration, or the tolerance of the algorithm should be greater than a very less value, 10 to the power minus 12. Then we will terminate this particular algorithm. Okay. Now we have to update the velocity update and the position update for the algorithm. So for this one, every time you know that the weight value, inertia weight is changing over here. That is, initial value is taken as 0.9 and final value is taken as 0.4, and it is reducing from 0.9 to 0.4 with respect to the iteration. So for that one, what is the optimal weight value? That is calculated with respect to each iteration. So that calculation is defined over here, that W is equal to, in this particular iteration, W is equal to W max minus W mean into present iteration divided by the maximum iteration. So this ITE present iteration, that is 1, and maximum iteration is 100, and W max, its initial value is the tolerance. How to about the tolerance, it is a very small value. You can take it as a very negligible value, close to 0. So the W max minus W mean, so into iteration divided by maximum iteration. So this decides the optimal weight of the problem, W. So now let's do the velocity update. So for every particle, I is equal to 1 to n, for j is equal to 1 to m, we are going to update the particle's velocity. So velocity is updated like this: weight into this previous velocity, plus C1 into rand, a random number, into the P best minus the present position. Okay. And then further, this is local best minus the present position, C2 into rand into global best minus the present position. Okay. So the difference now is getting calculated, and this is how the velocity will get updated. So once the velocity get updated, then you will update the position. So the position update, this you can write inside one loop only. But for your simplicity, I have written it two loops. So this xij is equal to xij plus bij. So the velocity and the positions get updated. So once this particular thing get updated, then you need to consider about certain things in PSO, that your particles are moving inside a particular boundary or within a particular limit. The particles are operating. They are not going away from the search space. That you have to keep them bind, because their velocity and positions, they are getting changed. There is a possibility that by moving here, there, they may go out of your bound. So from the maximum value to the minimum value, within that, you have to truncate all these particles. Okay. So over here, if the particle position, position is mainly responsible for everything. So if the position xij with this update has become lower than the minimum lower bound. So what is the minimum lower bound? LB. LB we have taken it as 0 for this particular problem. For another problem, it may be -1, it may be -2. What is the lower bound of the problem? So if the position, particle position is less than the lower bound, then you have to truncate that particle in that lower bound position. So xij is, if it is lower than LB, then it has to be truncated at LB. And if it is greater than upper bound, that means it is going beyond 2 pi maximum value. It is going, the particle position is going beyond 2 pi. Then also it does not possess any meaning for our problem. So you have to truncate it at the upper bound. So if it is xij is greater than upper bound, then xij is equal to the upper bound. So this you have to apply practically whenever you are designing the code. So now, once we have done it, the velocity and position have been updated and our particles fitness have been upgraded. So again, evaluating the fitness of the particle. So we have evaluated the fitness. Now we have to update the particle P best, that is their local best, we need to update, and their fitness also we need to update. So what is the importance about calculation of the P best? Now I will discuss with you. So originally we have this X this is the original position of the particle. Okay. Now this is F. Okay. So this is F1, F2, and F10. So this is original position of the particle, and this is the original fitness of the particle. Now, after the velocity update and the position update, then after first iteration, our particle position have been updated. So X is become X new. X new is equal to this X1 new, X2 new, and this x10 new. So it has become new update, and these new values, they will have different fitness because these positions are different, so they will have different fitness. So the fitness will be f new is equal to this f1n, f2n, and 10. So this is before updation and this is after updation. Okay. So among these, which one is the best that we are trying to calculate? That which one is the best? So F1 is best or F1n is best? Which one is best? Okay. How we will calculate which one is best? Sin x minimization value. So suppose F1 is minus 0.4. Okay. And F1n is minus 0.6. So among these two things, obviously it is a minimization problem. So minus 0.6 is better. So minus 0.6 is better means its corresponding position is what? X1n is its corresponding position. So my P best will be first is X1n. Now let's come to the second one. Suppose F2 is equal to 0.3 and here F2n is suppose is equal to 0.4. So which one is minimum? 0.3 and 0.4. So which is minimum? Obviously 0.3 is minimum. So the next one is this is minimum. So its corresponding position is x2. So x2 is taken into account, not x2n. You can observe the first one taken is x1n, whereas in the second one it is taken as x2 only, not x2n. Okay, so this is how you are going to calculate it for all the 10 particles. That is making out our local best or P best. And then how to calculate the global best? The global best is nothing but global best is best of P best. Best of P best is the global best. So this is how you calculate the updated P best as well as updated global best. Hope this idea is clear. The P best is always a vector, and G best is always a single entity. Remember this particular one. It is always a single entity. So now we will have a look at this programming aspect. So over here, now we are finding out, let's go to the code. So we are finding out the fitness. This was the original fitness and this is the updated fitness. Okay. F is the updated fitness and F0 is the previous fitness. So for all the particles, for I is equal to 1 to n, if your updated fitness is lesser than the initial fitness, okay, then the P best is equal to the thing is taken from the updated one. Otherwise, it lies as it is. So the F0 is equal to F1. So both the things have been updated. Now among these things, then we are going to find out which is the, as it is a iterative process. So for many number of runs when we are going to do it, so in each iteration, what is the minimum value? In each iteration, what is the minimum value that we are going to discuss? So over here, this is the minimum value of the fitness and its corresponding index that has been stored over here. The minimum value with respect to the run and with respect to the iteration, it has been stored in this particular variable. Okay. Now we are checking that if this updated F mean, the minimum value we have updated, that is better than the original value or not. If it has been better than the original value, then the G best we are updating with respect to its corresponding index term. Now, yes, some participant is asking why we are taking a tolerance value. It is not at all necessary that you use a tolerance value. Only with respect to iteration also you can run it for 100 iteration and solve the problem. But in some of the engineering problems, sometimes we require that if the problem minimum value, the error is less than this much threshold, then our objective is fulfilled. If the error is less than 0.005, then our algorithm needs to be stopped. We do not want lower than that particular thing. Okay. Suppose in a car manufacturing thing, we want the company should manufacture at least one car. So if the algorithm is giving the minimum value as one car, then we should stop our algorithm. We should not go below than that. Okay. So like that, the tolerance is taken into account. So here the tolerance is taken that the minimum value minus the FM minus the total minimum value, if it is very less than the tolerance value, then you can able to stop the algorithm. Otherwise, go on taking the iteration. So for each of the thing, the global best value we are storing in F value thing, the sign of global best value, that is the fitness value of, or what is the best value in that particular iteration, that we are storing over here, okay, over the run, and then displaying that particular final result, okay, the minimum value. So you can able to observe. Let me run this particular algorithm and show you the result. So you can observe, like yesterday, here also the PSO algorithm result is shown. I hope this is visible to you. In the y-axis, there is fitness function of the sin x, and in the x-axis, this is with respect to the iteration. So we have 100 iteration for which we are running the algorithm, and you can observe the algorithm is converging. It is getting minimized, and further minimized with respect to the iteration and reaching 100. So if we will run the algorithm again, it will not take the same path like this, but it will take a different path. So you observe again with this run, it has reached to -1, but earlier was reaching at at a 30 iteration. Now it is reaching at 18 iteration. So it depends upon how the initial random numbers you have generated. So for this particular thing, you will take a number of runs and corresponding thing, the average values you need to define. So this is how you run the PSO algorithm. I hope you have got the idea about the particle swarm optimization and the elapsed time it is showing. So now there is another algorithm I will be explaining you briefly. That is the differential evolution algorithm. So hope it is. So in differential evolution algorithm, the main important part is to generate independent random numbers. Okay. So here, this is again, in this particular algorithm, suppose we are considering X as the initial particles, then suppose X is considering X1, X2 up to X10, 10 thing. So here we have to generate in a very simple algorithm. I am saying the basic version of the differential evolution. In this, we need to pick 3 random numbers between 1 to 10. Okay. So suppose R1, R2, and R3. 3 random numbers we are generating between 1 to 10. Okay. So suppose the first random numbers comes out to be 2, then second is suppose 5, and third one is suppose 7. 3 numbers we have generated. Okay. Then from this initial vector, this is a solution, and we are calling it as initial vector. From this initial vector, we will create a mutated vector. In the differential equation, the first process is known as mutation. So we have to create a mutated vector. So how we will create a mutated vector? By taking the difference between two vectors and adding it to a third vector. So if we are considering this combination R1, R2, R3, then we will say that for the first element, what we will take for this mutated vector, first element, this M1 is equal to what? This R1 is 2, so its corresponding is x2 plus a constant. C is suppose a constant. Okay. So that constant is some 0.8 or some values you can able to take. Difference between this fifth and seventh will be added with this second one to generate a new vector. So this x5 minus x7. Are you getting my point? So this will create my first element. Corresponding to x1, there is a m1 I have generated. Similarly, corresponding to x2, I will again take 3 random numbers. Now the random numbers may be 1 and then 4, then maybe 9. Okay. When I am taking the x2, these 3 things may be 1, 4, 9. Then for m2, it will be x1 plus c into x4 minus x9. Clear? I hope it is clear. Then, like that, for this x10, again I will take 3 different values, random numbers, and I will create a m10. Fine. So you can able to generate this mutated vector from this initial vector. Okay. Then in the differential evolution, the next step is crossover. So in crossover, what is there? That you have to either based upon there is a condition is there. There is a mathematical condition is there. So if the condition is satisfied, you have to take values either from x1 or from m1. Okay. In the crossover operation, we are generating a crossover vector. So this crossover vector is suppose C. This is equal to either it will be x1 or it will be m1 based upon the condition. If the condition is satisfied, then it will be m1. If the condition is not satisfied, then it will be x1. Then like that, for the second one, again, you have to check the condition if it is satisfying or it is not satisfying. That means it is either taking a value from here or it will take a value from here based upon the condition of the crossover. Okay, the mathematical condition you know. So for the second one, again we will check that whether x2 is satisfying or m2 is satisfying. So like that, this will generate the particular crossover vector. Okay. Now, the third step, you have created this original vector. From the original vector, you have created this mutated vector. Then from the mutated vector, you have created this crossover vector. Okay. Now, the solution for next generation. Solution for next generation. Okay. So which one is best? Which one is best? So the crossover vector we have formulated. Okay. And we have created the mutant vector. We have created the original from the original vector. Original vector to mutant vector to crossover vector. So which one is best? The original X is best or this updated value is best? whichever is best, that will go for whether X1 is best or you are telling it as C1, suppose. C1 is best. Which is best? That will act as parent for the next. So similarly, X2 is best or C2 is best. So that you will go on comparing. So X10 is best or C10 is best. So you will go on comparing and pass on the solution to the next generation. So like that, generation by generation, it will go on repeating till the entire number of iteration gets satisfied. So hope you have understood the concept in a very simplified way. And we will have a look at this particular programming. So this is the thing of differential evolution. Here we have taken number of individual as 20. You can take it as a binary or you can take it as a real domain, no problem. So here it is a binary domain problem is taken. So in the binary domain, you can take it as 10-bit binary. So then again, you have to convert in the same way binary to decimal. So the random, like I told in the genetic algorithm, so the binary number that is again converted into 10-bit binary. So binary is being converted into decimal. So this is the 0 to 2 pi again sin x problem we are considering. So again binary to decimal it has been converted. And a is the converted into 2 to the power 9, 2 to the power 8 into 2 to the power 0. So that we have taken that particular one. This factor I have explained you that there is a constant to take the difference between two things will be added with the third thing to generate the new vector. So the difference and their percentage, that particular factor has been taken as 0.9. Okay. So now the thing has been converted into decimal values and then brought it into the particular range. Okay. So after bringing it into the range, now we will generate 3 random numbers. I told you 3 random numbers we are going to generate. That is very, very important. So first I have generated a random number, okay, between the range of the population 0 to 20. Then I have generated another random number. Okay. So now these 2 random numbers should never be equal. Okay. 3 random numbers should never be equal. So I am saying that if my second random number generated becomes equal to random number 1, then I should able to generate the random number 2 again. Then if I am generating another random number R3, okay, then I am checking the condition whether this R3 is equal to R2 or R3 is equal to R1. The third random number generated, first I have generated one random number R1, then second one when generated, I am checking second is equal to the first or not. If it is equal to, then I have to change that random number. Then a third random number I am generating, whether it is becoming equal to the second random number or whether it is equal to becoming the first random number. If in any case, if it is becoming equal to second random number or first random number, then I have to replace it again. Okay. So with this, I am generating R1, R2, R3, three random numbers which are completely different to each other. R1 will never equal to R2, will never equal to R3. That you have to make it sure. So now once after considering these values, these binary values have been converted into decimal and brought it into the range. So that is the same process, whatever we have done it yesterday. So three values have been done over here to the decimal and to its proper range. Now for creating this difference values, so you observe this is the line has been written for the difference between these two things. So the difference between these two vectors, its corresponding, this f got multiplied 0.9 of it and added to the first one to generate this particular vector. Okay, so this vector has been generated with this particular thing. The difference between these two multiplied with this and added with another one to generate this. So now we have, and this I is running in a loop, okay, and that is running for all the entire population. So for I is equal to 1, 2, 3, 4 up to 10 or 20, how many number of population has been generated? That many. So 10 number, suppose you have taken, then for each one you will generate a particular vector. Okay, so the first one corresponding to that first vector, second one to second vector, third one to third vector. Okay, so like that we have generated the mutant vector or the mutation vector or the perturbation vector, whatever you call it. Okay, so now you are observing that from this particular vector, the crossover operator. Okay, so the crossover operator, I told you a condition has to be satisfied, that the crossover rate we are considering it as 0.1. So for each particular thing, whether the thing, a random number is generated and this random number is less than equal to crossover, this is the condition I was telling, that whether it is less than this crossover or another random number generated, this j is equal to this random number generated a, okay, in the population. So j is the iteration that is running, that is becoming equal to a random number. So this is a condition that the, suppose I have now my iteration is this j is running from 1 to 20. So when you are taking it, suppose now j is equal to 3 and the random number generated is equal to 3 again. So then in that case, this particular condition will be satisfied. J is equal to A. The random number generated is 3. My present iteration is also 3. So the 3 and 3, that becomes equal. Okay. So J is equal to A. And the random number generated is less than CR. That is 0. Crossover rate is 0.01. So if this particular two condition gets satisfied, then you have to take the solution from the original one, from the updated one. Otherwise, you have to take the solution from the original case. So I told you the initial case and you have generated a mutated case. So for crossover, either you have to take it from the original or you have to take it from the updated one. So this is V1 is the updated one and SBin is the original one. So either we are based upon this condition satisfied, we are taking the new solution either from the updated one or from the original one. Okay, so like that we have generated our crossover output. Okay, so now again the crossover output, we have, this is again for converting the binary to decimal, same way. Then the selection for the next generation, whether the original one is best or the updated one is best. This AVU is the updated one and this AV is the original one. So which one is the best? This new vector we have created after crossover, that is giving us the best result, or the original thing that we have taken that is giving the best result. So for that one, we are comparing the thing. Okay. So now this is a sin x maximization problem. Maximum value of sin x. Okay. So for maximum value of sin x, you observe here the problem is maximum value of sin x. So that's why here when we are comparing the thing, you observe that we are going to compare the thing. If the function is greater than f1, so if the new generated function that is greater than the original one, then you take the thing. Otherwise, you keep the thing as it is original. So this is keeping the thing, the updated one with the original one. And this is updating the thing with the updated one. So if it is greater, the function, updated function is greater than this, okay, sin maximum. So whatever was existing, the updated one is greater than that, then you should update it with the new one. Otherwise, you should keep it with the old value. So this is the old value and this is the updated one. So with this, and go on repeating this particular thing until and unless you reach to the maximum number of iteration. Okay. So go on updating it. So then let's plot this particular one, plot the maximum value of fitness. So once you run the code, so you observe that this is an ideal case after running the code that we have obtained the one from the beginning of the problem. Okay. So D is a very good algorithm. So in maximum cases, it gives us very good results. So by chance, luckily, when I run it, it gives me one at the first iteration itself. So you observe that once it has reached one, so it is remaining stagnant at one only. So this is with respect to the iteration, and this y-axis is the fitness function value. So now again let's run it. So again run it. So you observe that it is increasing. It has changed the path. It has changed the path, and again it is trying to achieve the optimal solution. So when you run it repetitively, so you will get different path to achieve the maximum value. Okay. So I hope within this limited time, I could able to make you understand the concept as well as programming of both these algorithms. So this particular, in these codes, I have written step by step, and in each step, whatever is the process I am following, that I have explained it. For each variable also I have explained it. So once you go through this particular code, like yesterday's genetic algorithm code I have shared, so if you look at the code, then you can able to understand that each line, what is happening and what is the variable taken, what is its importance, everything I have given. So I believe you can able to find out more way of coding by yourself by doing it and practicing it. So that is how you will you are going to learn the coding. So I believe if you can able to code this genetic algorithm and particle swarm optimization and differential evolution, these three things in an effective manner, any of the next generation algorithms you can easily able to code them. Okay, so that much from my side for the presentation today. So thank you all. Good night.